Arrow of time. Time only moves forward. You age. You remember the past, but not the future. And no matter how much you wish otherwise, a broken egg never unbreaks. But why? The fundamental laws of physics don't actually require time to have a direction. So what forces time to march forward, never backward? This is the mystery of the arrow of time, one of the most puzzling questions in physics. At the core of this mystery is the second law of thermodynamics, which states that entropy always increases. Entropy is a measure of disorder, and the universe, it seems, is always moving towards more chaos. Ice melts, stars burn out, everything decays. This is the closest thing physics has to a rule that gives time a direction. The past is orderly, the future is messy. But here's the problem. The laws of physics work just as well in reverse. If you filmed an atom bouncing around and then played it backward, it would still obey all the known equations of motion. So why doesn't the universe behave like this on a larger scale? Why don't we see shattered glass reassemble or spilled coffee leap back into the cup? One explanation is that the Big Bang set the universe in an extremely low entropy state, like a neatly stacked deck of cards. Over time, disorder has increased, creating the illusion of time flowing forward. But this raises another question. Why did the Big Bang start in such an ordered state to begin with? And could time ever run backward under the right conditions? Some physicists speculate that in a distant, contracting universe, time could reverse, creating a mirror reality where everything runs backward. If that's true, then time isn't a fundamental force. It's just an effect of entropy. And if entropy could be controlled, could time be manipulated too? Cosmological Multiverse. What if the universe isn't the only one? What if, beyond the limits of what we can see, there are countless other universes, each with its own galaxies, laws of physics, and maybe even alternate versions of you? This is the idea behind the cosmological multiverse, a theory that suggests our universe is just one of many, part of a vast, ever-expanding cosmic landscape. The idea stems from cosmic inflation, the rapid expansion that took place moments after the Big Bang. Some physicists like Alan Guth and Andre Linde propose that inflation didn't just create our universe. It never stopped, continuing to spawn new universes forever. Each universe, or bubble, could have different physical constants, meaning the laws of nature we take for granted, like gravity or electromagnetism, might work completely differently elsewhere. But here's where things get controversial. There's no direct evidence. The multiverse isn't something we can observe, measure, or test, which raises a huge question. Is it even science? Critics argue that without experimental proof, the multiverse is nothing more than philosophical speculation dressed up in physics. Others counter that if inflation theory is correct, and much of modern cosmology relies on it, then the multiverse is an unavoidable consequence. If true, it would change everything. It could explain why our universe seems so perfectly fine-tuned for life. In an infinite multiverse, there would naturally be some universes where conditions are just right. But if we can never interact with these other realities, does it really matter? Is the multiverse a profound scientific breakthrough waiting to be understood, or just an escape hatch for ideas we can't explain? Until we find evidence, the answer remains beyond our universe, and maybe beyond our reach. Plate tectonics. The ground beneath your feet is moving, not fast enough to notice, but slowly, relentlessly reshaping continents, raising mountains, and tearing open oceans. This is plate tectonics, the unceasing motion of Earth's crust that explains why earthquakes shake cities, why volcanoes erupt, and why entire landmasses drift apart over millions of years. But for a long time, scientists dismissed this idea as pure nonsense. Before the 20th century, continents were believed to be fixed in place. Then came Alfred Wegener, a German meteorologist who noticed something odd. The coastlines of South America and Africa fit together like puzzle pieces. He proposed that continents weren't fixed at all, but drifted across Earth's surface over time. His idea, called continental drift, was ridiculed. He had no explanation for how massive land masses could move. It just didn't seem possible. Decades later, under the ocean, geologists discovered mid-ocean ridges, huge underwater mountain chains where new crust was forming. As molten rock rose from beneath, it pushed old crust away, slowly driving the continents apart. This discovery confirmed what Wegener had theorized all along. Earth's surface wasn't fixed. It was broken into giant plates constantly shifting and colliding. But not everyone accepted it immediately. Some scientists argued that if plates are always moving, why isn't the Earth ripping itself apart? Others questioned whether subduction, where one plate sinks beneath another, could actually recycle crust fast enough to balance the process. Even today, there are debates about what drives the movement of these plates. Is it the heat from Earth's core, or something even deeper? Plate tectonics explains earthquakes, volcanoes, and even the rise and fall of ancient supercontinents. But if Earth's crust is always shifting, what does that mean for our future? Could entire continents one day collide again, forming a new supercontinent? And if so, what will the world look like millions of years from now? Mind, origin of the moon. Look up at the night sky and you'll see it. The moon, Earth's closest companion. But have you ever wondered where it actually came from? For something that's been around for over 4 billion years, its origin remains one of the most debated mysteries in science. For decades, scientists have tried to piece together the moon's origin story, but no single explanation fits perfectly. Some early theories suggested it simply formed alongside Earth from the same swirling cloud of dust and gas. Others argued that Earth captured the moon, pulling in a wandering rock from space. The problem: neither fully explains why the moon's composition is eerily similar to Earth's crust, yet missing certain elements. Then came the giant impact hypothesis, now the leading theory. According to this idea, around 4.5 billion years ago, a Mars-sized planet, Theia, crashed into the young Earth. The collision was so violent that molten rock and debris were blasted into space, eventually coalescing to form the moon. This explains why the moon shares Earth's chemistry, but with key differences. Volatile elements were likely burned off in the fiery impact. But even this widely accepted theory has problems. Some scientists argue that if Theia truly existed, why haven't we found distinct chemical traces of it? Others suggest alternative ideas, like the moon forming from multiple smaller impacts or even being spun out of Earth itself due to extreme rotation, a theory once favored but now largely dismissed. No matter which theory turns out to be right, the moon's origin is more than just a cosmic curiosity. It could hold the key to understanding Earth's past and even the formation of other planets. So was it an impact, a cosmic accident, or something we haven't even thought of yet? The answer may be waiting on the moon itself. Mechanisms of photosynthesis. Without photosynthesis, life as we know it wouldn't exist. Every breath of oxygen, every bite of food, every towering tree, all of it depends on this biological magic trick that turns sunlight into energy. But here's the catch. We still don't fully understand how it works. Sure, we know the basics. Plants take in carbon dioxide and water, use sunlight to trigger a series of chemical reactions, and release oxygen while producing glucose. Simple enough, right? Not even close. The molecular machinery inside plants is mind-bogglingly complex, operating with near-perfect efficiency far beyond anything human engineers have ever built. And here's where the real controversy starts. For years, scientists believed that photosynthesis followed a straightforward step-by-step pathway. Light gets absorbed, energy gets transferred, and chemical bonds get formed. But recent discoveries suggest that quantum mechanics may be at play. Some studies indicate that plant cells don't just transfer energy like a baton in a relay race. They may use quantum superposition to explore multiple pathways at once, choosing the most efficient route. If true, this would mean that plants have unknowingly been harnessing the bizarre rules of quantum physics for billions of years. Not everyone is convinced. Skeptics argue that quantum effects are too delicate to survive in the messy, warm environment of a living cell. Others insist that classical physics alone is enough to explain photosynthesis without the need for exotic quantum phenomena. The debate continues, with experiments pushing the limits of what we thought plants were capable of. If we could unlock the full potential of photosynthesis, we could revolutionize energy production, perhaps even creating artificial leaves that could power entire cities. But before we get there, one question remains. Have plants mastered physics in ways we're only beginning to understand? Quantum effects in chemistry. Most of us think of chemistry as predictable. You mix two chemicals and they react. Simple. But what if I told you that some of the most important chemical reactions might be happening because of quantum physics? That at the tiniest scales, the world of molecules isn't as straightforward as it seems? This idea that quantum effects play a fundamental role in chemistry is both fascinating and controversial. Traditional chemistry operates on the laws of classical physics. It explains how atoms bond, how reactions occur, and how energy moves through molecules. But at extremely small scales, things start to get weird. Particles don't behave like tiny billiard balls. They behave like waves, existing in multiple places at once, tunneling through barriers they shouldn't be able to cross, and even choosing the most efficient reaction pathways, as if they knew the best route in advance. One of the most intriguing examples of this is enzyme catalysis, the process that speeds up chemical reactions inside your body. Some researchers believe that enzymes might be using quantum tunneling, a bizarre phenomenon where particles slip through energy barriers instead of climbing over them. If true, this means your body's chemistry relies on quantum tricks to function efficiently. And then there's photosynthesis. Some experiments suggest that the way plants transfer energy might involve quantum coherence, where energy exists in multiple states at once, finding the quickest route to the reaction center. If plants are secretly quantum physicists, what else in nature might be using these effects? Of course, skeptics argue that biological systems are too chaotic, too warm for delicate quantum phenomena to survive. They believe classical physics alone can explain chemistry. But the more we study these effects, the more we realize nature might be playing by quantum rules in ways we never imagined. If quantum mechanics is deeply embedded in chemistry, it could redefine how we think about everything, from drug design to renewable energy. But the real question is, if life itself is quantum, what else are we missing? Nature of chemical bonding. What if I told you that the very glue holding the universe together, chemical bonds, is still not fully understood? You'd think that by now we'd have figured out exactly how atoms stick together, right? Well, not quite. The nature of chemical bonding remains one of the most debated and mysterious topics in chemistry. At first glance, chemical bonds seem simple. Atoms share, steal, or swap electrons, forming stable molecules. This is what we were all taught in school. Ionic bonds involve electron theft. Covalent bonds involve sharing. And metallic bonds create electron seas. Case closed, right? Not exactly. Take covalent bonding, a fundamental concept. Traditional chemistry says atoms share electrons to form stable pairs. But quantum mechanics throws a wrench into this explanation. Electrons don't orbit like tiny planets. They exist in fuzzy probability clouds. In reality, when two atoms bond, their electrons don't just pair up in a straightforward way. They enter a strange quantum superposition, where they are spread out over both atoms at once. So do molecules even have bonds in a classical sense, or are they just complex quantum interactions? And then there's the mystery of the hydrogen bond. This weak attraction between molecules is responsible for everything from water's unique properties to the structure of DNA. But is it even a bond at all? Some scientists argue it's more of an electrostatic force, while others believe quantum tunneling and entanglement may be playing a role. These questions aren't just theoretical. Understanding chemical bonding at a deeper level could revolutionize material science, nanotechnology, and even drug design. The problem? We still don't have a unified theory that fully explains all types of bonding in every situation. So what if our entire understanding of how matter holds together is incomplete? What else might we be missing? Existence of black holes. Black holes shouldn't exist, at least not according to common sense. Imagine an object so dense, so powerful that not even light, the fastest thing in the universe, can escape its grasp. It sounds more like a cosmic horror story than real physics. And yet, black holes are one of the most fascinating and controversial topics in science. The idea of black holes first emerged from Einstein's general relativity. His equation suggested that if enough mass is packed into a small enough space, gravity would become so intense that it would create a one-way exit from the universe. But even Einstein himself was skeptical. He thought nature wouldn't allow such extreme objects to exist. Fast forward a century, and we now have mountains of evidence suggesting they are real. We've seen the effects of black holes on surrounding stars, detected gravitational waves from their collisions, and even captured the first ever image of one, a glowing ring of light surrounding a cosmic abyss. But here's where it gets weird. Do we truly know what's inside a black hole? Current physics says the core collapses into a singularity, a point of infinite density where all known laws of physics break down. But that's a problem. Infinite density makes no sense. Some scientists argue that black holes might not be what we think they are. Could they be wormholes, cosmic holograms, or something even stranger? Hawking's famous black hole information paradox suggests that these objects might be destroying information, something that violates fundamental laws of quantum mechanics. If black holes aren't what we think, then what are they? And if they do break physics, does that mean our entire understanding of the universe needs to be rewritten? Kuiper Belt and Oort cloud. Beyond Neptune lies a cosmic graveyard, an icy wasteland of forgotten worlds and ancient relics from the birth of the solar system. This is the Kuiper Belt, a region teeming with frozen debris, dwarf planets, and possibly answers to some of the biggest mysteries in astronomy. But if you go even farther, past the reach of our telescopes, you enter the Oort cloud, a hypothetical shell of icy bodies that may be the birthplace of long-period comets. These two regions challenge everything we thought we knew about the structure of our solar system. The Kuiper Belt is real. We've seen it. It's home to Pluto, Eris, and countless other icy objects, remnants from the chaotic formation of our cosmic neighborhood. It's often compared to an asteroid belt, but it's far larger, extending up to 50 times the distance between Earth and the Sun. The Oort cloud, however, is different. It's purely theoretical. No one has ever directly observed it. Yet many scientists believe it must exist because comets like Halley's or Hale-Bopp had to come from somewhere beyond the Kuiper Belt. Here's where it gets interesting. If the Oort cloud is real, it could stretch up to a light year from the Sun, meaning the outer edges might be influenced by passing stars or even interstellar objects. Some researchers speculate that the Oort cloud might contain rogue planets, orphaned worlds flung out of their original systems, drifting in the dark. But there's another mystery lurking in the Kuiper Belt, something astronomers call Planet 9. Some strange gravitational effects suggest that a massive hidden planet, several times the size of Earth, might be lurking out there, waiting to be found. If we ever confirm the Oort cloud's existence or find Planet 9, it could completely reshape our understanding of the solar system. But until then, the outer reaches of our cosmic backyard remain an unsolved enigma, silently orbiting in the frozen dark. Nature of gamma-ray bursts. If Earth were unlucky enough to be in the path of a gamma-ray burst, civilization could be wiped out in seconds. These are the most powerful explosions in the universe, unleashing more energy in a few moments than the Sun will in its entire lifetime. But what exactly causes them? And could one ever be aimed at us? Gamma-ray bursts, or GRBs, were first discovered by accident in the 1960s. During the Cold War, U.S. satellites designed to detect nuclear explosions started picking up mysterious flashes of high-energy radiation from deep space. At first, the source was unknown, and for decades, scientists debated whether these were the signatures of exotic supernovae, colliding neutron stars, or something even stranger. Today, the leading theories suggest that there are two main types of gamma-ray bursts. The long-duration bursts, lasting more than 2 seconds, likely come from massive stars collapsing into black holes. The short bursts, lasting just milliseconds, are thought to be the result of neutron stars or black holes merging. Both events produce incredibly focused jets of energy that, if aimed directly at Earth, could sterilize entire planets. The controversy: we still don't fully understand them. Some bursts behave in ways that don't fit current models, leading some physicists to speculate that unknown physics, perhaps even exotic dark matter interactions, could be involved. Others wonder if some GRBs could be artificially created, a terrifying prospect that hints at the existence of ultra-advanced civilizations. Could a gamma-ray burst ever hit Earth? So far, no direct threats have been detected. But if one did, it could cause a mass extinction event worse than the asteroid that wiped out the dinosaurs. So are we safe? Or is the universe hiding a cosmic sniper waiting to fire? Dark matter halos. Galaxies are spinning too fast. Based on what we know about gravity, many of them should have torn themselves apart long ago. But they haven't. Something invisible is holding them together. That something is what we call dark matter halos, massive, unseen structures that act as cosmic scaffolding, shaping galaxies and even the universe itself. Unlike regular matter, dark matter doesn't emit, absorb, or reflect light, making it impossible to see directly. Yet its gravitational influence is undeniable. Galaxies move as they are embedded in vast spherical halos of dark matter far larger than the galaxies themselves. These halos are thought to be the cosmic glue that keeps galaxies from flying apart, explaining discrepancies in their motion that ordinary physics can't account for. But here's the controversy. We still have no idea what dark matter actually is. The leading theories suggest it could be made up of exotic particles like WIMPs, weakly interacting massive particles, or axions, ghostly entities that barely interact with normal matter. Others argue that dark matter doesn't exist at all, and instead, we need to modify our understanding of gravity itself. A theory called modified Newtonian dynamics, MOND, suggests that gravity behaves differently at galactic scales, eliminating the need for dark matter altogether. So are dark matter halos the invisible architects of the cosmos? Or are we fundamentally misunderstanding how gravity works? If dark matter exists, finding it could revolutionize physics. If it doesn't, then the laws of the universe may need to be rewritten. Which possibility is more unsettling? Interstellar Medium. Space is not empty. It may look like a vast, silent void, but in reality, it's filled with an invisible, ever-changing substance known as the interstellar medium, a mix of gas, dust, and charged particles stretching between the stars. Without it, galaxies wouldn't exist. Stars wouldn't form. And the universe as we know it would be drastically different. The interstellar medium, or IZEM, is often called the cosmic nursery because it's the birthplace of new stars. Clumps of gas collapse under gravity, forming glowing new suns, while leftover material drifts through space waiting for its turn to create something new. But this interstellar soup is also responsible for something far more mysterious: the way galaxies evolve over billions of years. Here's where things get controversial. The IZEM is full of strange phenomena we still don't fully understand. It contains massive, unseen magnetic fields that seem to influence the motion of gas clouds, yet we have no idea where they come from. Some scientists argue that dark matter interacts with the ISM in ways we haven't detected. Others suggest that cosmic rays, high-energy particles speeding through space, shape the interstellar medium in ways that defy our current physics models. Even more puzzling is how the ISM affects star death. Supernovae, massive star explosions, send shockwaves through this medium, triggering more star formation. But some researchers believe these explosions can halt star birth instead, choking off galaxies from making new stars altogether. So is the interstellar medium a cosmic life giver, a silent killer, or both? Its effects are so complex that we're still piecing the puzzle together. But one thing is certain, space is far from empty. The real question is, what else is hiding in the invisible fabric between the stars? Mechanisms of star formation. Stars are born in chaos. Deep in the coldest, darkest regions of space, invisible clouds of gas and dust drift aimlessly for millions of years until something disturbs them. A passing star, a collision of galaxies, or the shockwave of a distant supernova sends ripples through space, compressing the cloud and igniting a slow but inevitable chain reaction. And just like that, a new star begins to form. But here's where things get complicated. While we understand the general process, the exact mechanisms of star formation are still a subject of debate. Gravity pulls the gas together, heating it up until nuclear fusion ignites. But why do some clouds collapse into massive stars while others barely manage to spark? Why do some regions of space form clusters of stars while others remain barren? These are questions astrophysicists are still struggling to answer. One of the biggest mysteries is turbulence. Gas clouds in space aren't just floating serenely, they're chaotic, moving in unpredictable patterns. Some theories suggest that turbulence plays a major role in determining which clouds will collapse and which won't. Others argue that magnetic fields threading through these clouds resist collapse, slowing down the process. In fact, some scientists believe that without magnetic forces, stars would form much faster, perhaps too fast for galaxies to sustain themselves. Another controversy: the role of dark matter. Some researchers suggest that unseen dark matter clumps could act as gravitational anchors, pulling gas together and triggering star birth. If true, this would mean star formation isn't just a process of normal matter, but is intimately tied to one of the greatest cosmic mysteries of all time. Despite these debates, one thing is certain. Without star formation, the universe would be nothing but a cold, lifeless void. Every planet, every element, every living thing owes its existence to a cloud of gas that collapsed billions of years ago. But if the exact rules of star formation are still unclear, how many other cosmic processes are we still completely in the dark about? Origin of the solar system. The solar system didn't just appear. It had to be built. But how do you take a cloud of dust and gas floating in space and turn it into planets, moons, and an entire star system? Scientists think they have the answer, but the details of how it all happened are still up for debate. The most widely accepted theory is the nebular hypothesis. Around 4.6 billion years ago, a massive cloud of gas and dust, left over from previous generations of stars, collapsed under its own gravity. As it shrank, it started spinning faster, flattening into a swirling disk with a dense hot center. That center ignited, forming the sun, while the remaining material clumped together to create planets, moons, asteroids, and everything else in our solar system. Sounds simple, right? Not exactly. There are some problems. Why do some planets have weird orbits? Why did the gas giants, Jupiter and Saturn, form so far from the sun while rocky planets like Earth and Mars stayed close? And what about the late heavy bombardment, a period when massive asteroids rained down on the planets? Some scientists think it was caused by Jupiter and Saturn shifting their orbits, disrupting everything in their path. But others argue this event may not have even happened at all. Then there's the question of how the gas giants formed so quickly. Standard models suggest they needed millions of years to collect enough material. But recent evidence suggests they may have formed in just a few thousand years, far too fast for conventional theories to explain. While we've pieced together a rough timeline, the finer details remain a mystery. And if we still don't fully understand how our own solar system formed, how can we be sure we truly understand the process in exoplanetary systems across the universe? Safety and efficacy of vaccines. Vaccines are one of the greatest medical achievements in human history, credited with saving millions of lives and eradicating deadly diseases. And yet, they remain one of the most hotly debated topics in modern science. How can something so essential also be so controversial? The science behind vaccines is simple but brilliant. By exposing the body to a weakened or inactive form of a virus, the immune system learns how to fight it off without actually getting sick. This prepares the body for the real thing, making infections far less severe or preventing them altogether. Smallpox, a disease that once killed millions, was wiped out entirely because of vaccines. Polio, which used to paralyze children worldwide, is now incredibly rare. But despite their success, vaccines have also been the subject of intense skepticism. Some concerns stem from historical failures, like the Cutter incident in 1955, where improperly inactivated polio vaccines caused infections instead of preventing them. Others come from a now debunked 1998 study falsely linking vaccines to autism, a claim that spread like wildfire despite being completely discredited. The debate isn't just about science. It's about trust. Some argue that pharmaceutical companies and governments haven't been transparent enough, fueling suspicion. Others worry about rare side effects, even though the risks of vaccines are statistically far smaller than the diseases they prevent. And then there's the question of herd immunity. Should vaccination be a personal choice or a public responsibility? At its core, the controversy over vaccines isn't just about medicine. It's about how we weigh risk, trust science, and make decisions for society as a whole. And as new diseases emerge, one question remains. Can we afford to ignore a tool that has saved so many lives? Origin of the elements. Everything around you, the air you breathe, the water you drink, even your own body, is made from a collection of elements. But where did those elements come from? Why does the universe have hydrogen, carbon, gold, and uranium instead of nothing at all? The answer is buried deep in the heart of stars, supernovae, and the very fabric of the cosmos itself. Scientists believe that the elements were forged in a sequence of violent, universe-shaping events. The lightest elements, hydrogen and helium, were born moments after the Big Bang. But the heavier ones, the oxygen in your lungs, the iron in your blood, the gold in your jewelry, came from something far more extreme, the death of stars. Inside the cores of massive stars, atoms smash together, fusing into heavier elements. When those stars explode as supernovae, they scatter these elements across space, seeding the universe with the building blocks of planets, life, and everything we know. But not everyone agrees on the exact details. Some physicists argue that neutron star collisions, not just supernovae, played a key role in producing the heaviest elements, like gold and platinum. Others suggest that the conditions for element formation might have been different in the early universe than we assume. Could unknown physics have shaped the periodic table in ways we still don't understand? No. This mystery is far from settled, and new discoveries keep challenging our assumptions. What if there are entirely different cosmic processes producing elements we haven't even considered? If the periodic table is our cosmic recipe book, we're still trying to figure out exactly how the universe wrote it. Origin of the cosmic microwave background. There's an invisible whisper from the birth of the universe stretching across the entire cosmos. A faint, persistent signal that exists everywhere all the time. It's not coming from stars, black holes, or galaxies. It's coming from the very beginning of time itself. This is the cosmic microwave background, CMB, and it might be the most important clue we have about the origins of the universe. The CMB is often described as the afterglow of the Big Bang, the remnant heat from a time when the universe was just a hot, dense soup of particles. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form, allowing light to travel freely for the first time. That light has been stretching and cooling ever since, eventually becoming the faint microwave radiation we detect today. This discovery was a game changer. In 1964, scientists Arno Penzias and Robert Wilson accidentally stumbled upon this signal while trying to eliminate interference from their radio telescope. Instead of noise, they had uncovered the oldest light in the universe, confirming key predictions of the Big Bang model. But here's where things get controversial. While most cosmologists accept the CMB as definitive evidence of the Big Bang, some dissenters argue that alternative theories, like the steady-state theory or cyclic universe models, could explain the data differently. Others debate whether unexplained anomalies in the CMB, like the so-called cold spot, hint at new physics or even parallel universes. So is the cosmic microwave background the final proof of the Big Bang? Or is it hiding something even more profound? If this is the universe's oldest signal, what else could it be telling us about reality itself? Existence of a molten core. Beneath your feet, just a few thousand kilometers down, lies a world of molten rock and searing metal, a vast, churning ocean of liquid iron that keeps our planet alive. At least, that's what most scientists believe. The existence of Earth's molten core is one of the most widely accepted ideas in geology. But here's the catch. No one has ever seen it. Unlike the surface of the moon, or even the depths of the ocean, we've never drilled deep enough to directly observe the core. The deepest hole ever drilled, the Kola Super Deep Borehole, only scratched about 12 kilometers down, just 0.2% of the way to the center. Everything we know about Earth's interior comes from indirect clues like seismic waves, magnetic fields, and computer models. Seismic data provides our strongest evidence. When earthquakes happen, they send shock waves rippling through the planet. Some waves can pass through liquid while others can't, creating a pattern that suggests a solid inner core surrounded by a molten outer core. This dynamic system is believed to generate Earth's magnetic field, shielding us from deadly cosmic radiation. Without it, life as we know it wouldn't exist. But not everyone is convinced. Some alternative theories propose that Earth's core might not be as molten as we think, or that different materials, perhaps even exotic unknown substances, exist deep inside. Others question whether we fully understand how Earth's magnetic field is generated, suggesting that new discoveries could rewrite what we think we know. If Earth's core is more complex than we imagined, what else might be hidden beneath the surface? Is our planet's heart still a mystery waiting to be unraveled? Or have we been staring at the answer all along? Mechanisms of enzyme catalysis. Your body is a high-speed biochemical factory where millions of reactions happen every second. But here's the mystery. Most of these reactions should take thousands, even millions of years to occur naturally, yet they happen almost instantly. How? The answer lies in one of nature's greatest tricks: enzymes, tiny biological machines that speed up reactions with near magical precision. At the core of this mystery is enzyme catalysis, the process by which enzymes accelerate chemical reactions. The traditional explanation follows the lock and key model, where the enzyme and its target molecule fit together perfectly. But things get strange when we dive deeper. For decades, scientists believed enzymes worked simply by stabilizing molecules and lowering the activation energy needed for reactions. But modern research suggests something even more bizarre. Enzymes may actually manipulate quantum mechanics to get the job done. Some experiments suggest that enzymes enable quantum tunneling, where particles skip over energy barriers instead of climbing them. This would mean that enzymes don't just speed up reactions, they bend the rules of classical chemistry. Not everyone agrees with this idea. Some researchers argue that more conventional physics, such as electrostatic interactions, fully explains enzyme efficiency. Others believe that enzyme evolution itself has fine-tuned them to exploit quantum effects, making them far more sophisticated than we ever imagined. If quantum tunneling is truly at play, it could reshape how we understand not just biology, but chemistry itself. Could the secrets of enzyme catalysis one day help us design super-efficient artificial enzymes or unlock new frontiers in medicine? Or are we still missing something even bigger? Stability of certain elements. Some elements are like ticking time bombs, constantly breaking apart while others sit calmly unchanged for billions of years. But why? What makes some elements stable, while others collapse in an instant? This question has led to one of the biggest mysteries in nuclear physics, the island of stability. In the periodic table, most elements beyond uranium are radioactive, meaning their atoms decay over time, sometimes in mere fractions of a second. The heavier an element gets, the more unstable it tends to be. But physicists believe that certain super-heavy elements, ones we've never even seen in nature, might be strangely stable, lasting seconds, minutes, or even longer than the age of the universe. The idea comes from nuclear shell theory, which suggests that atomic nuclei have magic numbers of protons and neutrons that make them extra stable, just like how electrons fill energy levels in atoms. If a super-heavy element lands on this so-called island of stability, it might resist decay far longer than expected. But here's the problem. We've never been able to synthesize one stable enough to prove it. Some scientists believe we're close, pointing to recent discoveries of elements like moscovium and oganesson, which hint that stability may increase as we push further into uncharted atomic territory. Others argue that this island is a mirage. Perhaps these elements exist, but only fleetingly, with lifetimes too short to be useful. If we do find a long-lived super-heavy element, it could redefine chemistry and nuclear physics, opening doors to new materials, energy sources, or even undiscovered laws of nature. Could we one day engineer an element more stable than anything found on Earth? Or are we chasing an illusion, hoping to hold on to something that was never meant to last? Concept of aromaticity. Some molecules refuse to behave the way they should. Instead of following the normal rules of chemical bonding, they form strange, ultra-stable rings with electrons that seem to float around freely. This is the essence of aromaticity, one of the most puzzling and fundamental concepts in chemistry. The term might make you think of pleasant smells. After all, many aromatic compounds like benzene were originally discovered in fragrant substances. But scientifically, aromaticity is about stability. Unlike most molecules which have fixed bonds between atoms, aromatic compounds share electrons across the entire ring structure, creating a weird cloud of electron density that makes them far more stable than expected. Here's where things get controversial. For decades, chemists believed that aromaticity followed a strict rule. A molecule must have a specific number of electrons in its ring, called Huckel's rule, to be aromatic. But then anti-aromatic compounds were discovered, structures that should have been stable but turned out to be highly reactive. Even more confusing, some molecules defied both categories, existing in a strange limbo between aromatic and non-aromatic states. Today, chemists debate whether aromaticity is even a binary property, or if it exists on a spectrum. Some molecules seem to switch between aromatic and non-aromatic states, while others challenge the very definition of what it means to be aromatic. Understanding aromaticity isn't just an academic exercise. It's the foundation of organic chemistry, material science, and even pharmaceuticals. Could we one day manipulate aromaticity to create super-stable materials or entirely new forms of chemistry? Or will we always be chasing a definition that refuses to be pinned down? Nature of chemical bonding. What if I told you that the very glue holding the universe together, chemical bonds, is still not fully understood? You'd think that by now we'd have figured out exactly how atoms stick together, right? Well, not quite. The nature of chemical bonding remains one of the most debated and mysterious topics in chemistry. At first glance, chemical bonds seem simple. Atoms share, steal, or swap electrons, forming stable molecules. This is what we were all taught in school. Ionic bonds involve electron theft, covalent bonds involve sharing, And metallic bonds create electron seas. Case closed, right? Not exactly. Take covalent bonding, a fundamental concept. Traditional chemistry says atoms share electrons to form stable pairs. But quantum mechanics throws a wrench into this explanation. Electrons don't orbit like tiny planets. They exist in fuzzy probability clouds. In reality, when two atoms bond, their electrons don't just pair up in a straightforward way. They enter a strange quantum superposition, where they are spread out over both atoms at once. So do molecules even have bonds in a classical sense, or are they just complex quantum interactions? And then there's the mystery of the hydrogen bond. This weak attraction between molecules is responsible for everything from water's unique properties to the structure of DNA. But is it even a bond at all? Some scientists argue it's more of an electrostatic force, while others believe quantum tunneling and entanglement may be playing a role. These questions aren't just theoretical. Understanding chemical bonding at a deeper level could revolutionize material science, nanotechnology, and even drug design. The problem: we still don't have a unified theory that fully explains all types of bonding in every situation. So what if our entire understanding of how matter holds together is incomplete? What else might we be missing? Mechanisms of atmospheric chemistry. Earth's atmosphere is a vast, swirling chemical laboratory, constantly reacting, shifting, and reshaping the conditions that make life possible. But despite our deep understanding of chemistry, there's one thing scientists still debate. How exactly do the countless chemical reactions in the atmosphere work, and what forces are shaping them? At first glance, atmospheric chemistry seems straightforward. Sunlight breaks molecules apart, oxygen reacts with pollutants, and weather moves everything around. But when you zoom in, things get weird. The air we breathe is filled with radicals, highly reactive molecules that exist for mere fractions of a second before disappearing into new compounds. Some of these reactions create the ozone layer, shielding us from deadly radiation. Others form acid rain, corroding cities and forests. And some, like the interplay of carbon dioxide, methane, and aerosols, determine Earth's climate itself. One of the biggest debates in atmospheric chemistry is about how human activity influences these reactions. We know that emissions from factories and cars change air quality, but predicting exactly how new chemicals will interact in the atmosphere is a challenge. For instance, scientists once thought CFCs, chlorofluorocarbons, were harmless until they were found to be destroying the ozone layer. What other invisible dangers are we missing? Then there's the mystery of climate feedback loops. Do certain atmospheric reactions amplify warming or help cool the planet? And how much do natural processes, like volcanic eruptions or plant emissions, contribute compared to human-made pollutants? If we could fully decode the chemistry of our atmosphere, we might find ways to engineer cleaner air, prevent climate disasters, or even terraform other planets. But until then, the air around us remains an unpredictable, ever-changing puzzle, one we're still racing to solve. Existence of quasicrystals. Crystals are supposed to follow rules, perfectly repeating patterns of atoms forming precise structures. But what if nature had been hiding a completely different kind of order, something that defied everything we thought we knew about solid matter? This is the strange world of quasicrystals, materials that shouldn't exist, yet somehow do. For decades, scientists believed that all crystals had translational symmetry, meaning their atomic structures repeated predictably, like tiles on a bathroom floor. But in 1982, Israeli scientist Dan Shechtman discovered something that shattered this assumption. He found a material with an ordered atomic structure that never repeated, arranged in a way that was mathematically impossible, or so everyone thought. The discovery was met with ridicule. Crystallography textbooks stated with certainty that quasicrystals couldn't exist. Shechtman was even laughed at by colleagues and told to go read a book on solid-state physics. For years, the scientific community rejected his findings. But as more researchers examined the evidence, they realized that Schechtman was right. In 2011, he won the Nobel Prize in Chemistry for proving that quasicrystals were real. So why is this so controversial? Because it rewrote the fundamental understanding of solid matter. Quasicrystals challenge the traditional definition of what a crystal even is. They also appear in unexpected places. Some have been found in meteorites, hinting that nature may have created them long before we did. Now, scientists are exploring how quasicrystals could be used in everything from non-stick coatings to ultra-hard materials. But their existence still raises deeper questions. Are there other unknown forms of matter waiting to be discovered? What other impossible structures might nature be hiding from us? Molecular machines. Imagine machines so small that they could fit inside a single cell, repairing DNA, delivering drugs directly to diseased tissues, or even assembling molecules with atomic precision. These aren't science fiction. They're molecular machines, and they could revolutionize medicine, technology, and even the way we think about life itself. Molecular machines are nanoscale structures that move, rotate, and perform mechanical tasks, just like the gears and levers in a watch, except they operate at the scale of individual molecules. Some already exist in nature. Take ATP synthase, an enzyme found in cells that spins like a microscopic turbine to produce energy. Or kinesin proteins, which literally walk along cellular highways carrying vital cargo. But what if we could design and build our own molecular machines? Scientists are now developing synthetic versions, tiny molecular motors that can be controlled by light, electricity, or chemical reactions. In 2016, this work won the Nobel Prize in Chemistry, marking a huge leap toward a world where artificial molecular machines could be used for everything from targeted drug delivery to creating self-repairing materials. So why is this controversial? Because if we can engineer molecular machines, could we one day create self-replicating ones? The idea of nanobots multiplying uncontrollably inside the body or environment sparks both excitement and fear. Some researchers worry about unintended consequences, while others argue we are still far from that reality. But one thing's certain, molecular machines have already begun to blur the lines between biology and technology. Could we one day build a fully synthetic life form from scratch? If nature has spent billions of years perfecting molecular machines, how long will it take for us to catch up? No, role of volcanism in climate. There's a force on Earth that has shaped entire continents, wiped out species, and even altered the course of human history, all without a single conscious thought. Volcanoes. They're not just fiery mountains. They might be one of the most powerful climate influences on the planet. Some scientists even argue that volcanic eruptions have played a bigger role in shaping Earth's climate than we ever realized. Volcanoes release massive amounts of gases and particles into the atmosphere. Some, like carbon dioxide, trap heat and contribute to global warming. Others, like sulfur dioxide, reflect sunlight and cause cooling. A single large eruption can lower global temperatures for years. The 1815 eruption of Mount Tambora in Indonesia was so massive that it triggered the year without a summer, plunging temperatures, ruining crops, and leading to widespread famine. But here's where the controversy begins. Some researchers believe volcanic activity has contributed to long-term climate change, even playing a role in past ice ages. Others argue that while individual eruptions can cause short-term cooling, their impact is insignificant compared to human-driven carbon emissions. The biggest debate: whether modern climate change models properly account for volcanic influences. Some claim they overestimate the role of CO2 while underestimating volcanic effects. If volcanoes have altered climate before, could they do it again? And more importantly, could we one day harness this natural force? Perhaps even trigger small eruptions to cool the planet intentionally? A wild idea. But considering how much power volcanoes already have, maybe nature has been running its own climate experiments all along. Future of ice sheets. The fate of the world's ice sheets could decide the future of civilization itself. These vast frozen landscapes hold enough water to reshape coastlines, drown cities, and alter global weather patterns in ways we're only beginning to understand. But just how much ice will melt, and how fast, remains one of the most controversial questions in climate science. Greenland and Antarctica contain 2/3 of the planet's fresh water, locked away as ice. If they were to melt completely, sea levels could rise by over 200 feet, turning major cities into underwater relics. But that's not the only concern. As ice sheets break apart, they disrupt ocean currents, affect weather systems, and even influence the Earth's rotation. The real debate lies in how quickly this process is unfolding. Some scientists argue that we've already passed the tipping point, with irreversible melting underway. The evidence? The collapse of ice shelves in Antarctica, the accelerating flow of glaciers, and the discovery that warming water is eating away at ice from below. Others believe there's still time, that the ice sheets are more resilient than we think, and that stabilizing global temperatures could slow or even halt their retreat. But here's the real question. What happens if we're wrong? If ice loss is faster than predicted, we could see catastrophic flooding within our lifetimes. Could we find a way to refreeze the poles, redirect ocean currents, or will future generations simply have to abandon the coasts and move inland? One thing is certain, the fate of our ice sheets isn't just a scientific mystery. It's a question of survival. Possibility of a supercontinent. Earth's continents are drifting, but where are they going? Right now, the continents are scattered across the globe, but geologists believe they are slowly moving toward a future supercontinent, one that could reshape life on Earth in ways we can barely imagine. This isn't just speculation. It has happened before. Hundreds of millions of years ago, all land on Earth was fused together in a massive supercontinent called Pangaea. Over time, it broke apart, creating the continents we know today. But plate tectonics never stops. Continents are constantly shifting, moving at about the same speed as your fingernails grow. In another 200 to 300 million years, they could collide again, forming a new supercontinent. There are several competing models for what this might look like. One idea, called Pangaea Proxima, suggests that the continents could slowly drift back together into one massive landmass near the equator. Another, called Amasia, predicts that North America and Asia could merge at the North Pole. Meanwhile, the Novo Pangaea model envisions a completely new land arrangement, driven by changes in ocean currents and plate motion. But what would this mean for life on Earth? A supercontinent could drastically alter climate patterns, potentially creating vast deserts or extreme weather zones. It could also disrupt ocean currents, reshaping ecosystems, and possibly even triggering mass extinctions. Some scientists argue that predicting plate tectonics millions of years into the future is impossible due to the chaotic nature of the process. Others believe the models are solid, based on how the continents have behaved in the past. If Earth is heading toward another supercontinent, what will the world look like? Will it be a paradise of connected land masses or a hostile environment of extreme conditions? And if humans are still around, will we adapt, or will we need to find another home? Causes of earthquakes. The ground beneath your feet is not as solid as it seems. In an instant, the Earth can shake violently, tearing apart cities, triggering tsunamis, and reshaping landscapes. But what actually causes earthquakes? And why do some scientists believe there's more to them than just shifting tectonic plates? The most widely accepted explanation is plate tectonics. The Earth's crust isn't a single solid shell. It's broken into massive pieces called tectonic plates that float on a layer of molten rock. As these plates move, they grind against each other, get stuck, and build up stress. When that stress finally releases, the result is an earthquake. Simple, right? Not always. Some researchers argue that not all earthquakes fit neatly into this model. For example, deep earthquakes, those occurring more than 300 miles below the surface, happen in areas where rocks should be too hot and soft to store enough stress to rupture. Scientists suspect other forces may be at play, such as mineral transformations that release energy deep within the mantle. Then there's the theory that earthquakes might not always be natural. Human activity, such as fracking, dam construction, and deep mining, has been linked to unexpected seismic activity. Some earthquakes have even occurred in places where tectonic movement isn't common. Could human actions be creating artificial fault lines? And here's where things get even stranger. Some researchers speculate that electromagnetic shifts or even solar activity might have subtle influences on earthquake patterns. While mainstream geology doesn't fully embrace these ideas, they continue to be explored. So are earthquakes simply the product of grinding plates, or is there more to the story? If our planet is constantly shifting, what unknown forces might still be waiting to shake up our understanding of how the Earth really works? Mechanisms of mountain formation. Mountains are Earth's greatest sculptures. But how exactly are they formed? Most people assume mountains have always been there, standing tall and unshakable. But in reality, they are dynamic, constantly growing, eroding, and even vanishing over millions of years. The real question is, what forces are powerful enough to push entire landscapes miles into the sky? The standard explanation ties mountain formation to plate tectonics. When massive sections of Earth's crust, called tectonic plates, collide, the land has nowhere to go but up, creating enormous mountain ranges like the Himalayas. The collision between the Indian and Eurasian plates, for example, continues to push Mount Everest higher by a few millimeters each year. But is this the whole story? Some scientists argue that mountains don't just form from plate collisions. Some may rise due to forces from deep within the Earth. Mantle plumes. Rising columns of superheated rock could be responsible for uplifting vast regions. Others suggest that intense erosion and climate changes may contribute, reshaping landscapes in ways we don't fully understand. Then there's the debate over ancient mountain ranges. If plate tectonics explains modern mountains, why do we find evidence of ancient mountain belts in places where no major tectonic activity exists today? Could there be missing geological processes at play? Mountains hold the history of Earth's violent past, and yet their formation is still full of mysteries. Are there hidden forces shaping the land beneath us? Or do we already have all the answers but just need to dig a little deeper, perhaps beneath our very feet? Role of asteroids in Earth's history. What if Earth's history was shaped not by slow, gradual changes, but by sudden, cataclysmic impacts from space? Asteroids, those wandering space rocks, have a reputation for destruction, but their role in shaping our planet might be far greater than we ever imagined. Some scientists argue that without them, life as we know it wouldn't even exist. The most famous example? The Chicxulub impact, the asteroid that wiped out the dinosaurs 66 million years ago. When this 6-mile-wide rock slammed into what is now Mexico's Yucatan Peninsula, it unleashed destruction on a planetary scale. Shockwaves, wildfires, tsunamis, and a cloud of debris that plunged Earth into darkness. Without that impact, mammals, our ancestors, might never have taken over. But that's just one theory. Some researchers believe asteroids didn't just wipe species out, they may have also helped create life. Early Earth was bombarded by space debris, and some scientists think these impacts may have delivered water, organic molecules, and even the building blocks of life itself. Or, if that's true, then the very event that nearly wiped out life millions of years ago could be the same force that made it possible in the first place. Not everyone agrees. Some argue that Earth's geology and volcanic activity played a bigger role in extinctions and climate changes than asteroid impacts ever did. Others suggest that asteroid-delivered organic molecules weren't necessary, that life could have emerged from Earth's own chemistry. So which is it? Are asteroids cosmic harbingers of doom or essential ingredients for life's creation? If another impact were headed our way today, would it mark the end or the beginning of something new? The theory of evolution is still one of the most controversial theories in science. It radically changed our belief about how humans came into existence. For most of history, people thought life was fixed, unchanging, designed with purpose. Then this idea came along and rewrote everything we thought we knew. In 1859, Charles Darwin published On the Origin of Species, introducing a concept so disruptive it reshaped biology forever: evolution by natural selection. The idea was simple but groundbreaking. Organisms with traits that help them survive and reproduce are more likely to pass on those traits. Over time, tiny changes accumulate, leading to entirely new species. This wasn't guided by any higher force, just the raw mechanics of survival. But evolution didn't just challenge scientific ideas, it challenged humanity's place in the world. If we weren't created in our current form, what did that mean for our significance? Were we just another species shaped by time and adaptation? The reaction was explosive. Religious groups rejected it. Some scientists doubted whether natural selection alone could explain the complexity of life. Even today, despite overwhelming fossil, genetic, and observational evidence, evolution remains one of the most debated topics in science, with creationism and intelligent design still holding strong influence in certain communities. Yet evolution is now a cornerstone of modern science. It shapes our understanding of genetics, medicine, and even artificial intelligence. But if evolution has shaped us so far, what happens next? Are we still evolving? And if so, into what? Heliocentrism. For centuries, people believed that Earth was the center of everything. The sun, moon, and stars all revolved around us in perfect divine harmony. But then one idea changed everything: heliocentrism, the radical claim that the Earth isn't the center of the universe, but rather orbits the sun. Today, this sounds obvious, but at the time, it was one of the most dangerous and controversial scientific ideas ever proposed. The story begins with Nicolaus Copernicus, a 16th century astronomer who dared to challenge the long-accepted geocentric model, which had been supported for centuries by the Catholic Church and philosophers like Aristotle and Ptolemy. Copernicus argued that the Earth, along with the other planets, revolved around the sun. But this wasn't just an academic debate. This idea shook the foundations of power, religion, and humanity's place in the cosmos. At first, heliocentrism was dismissed as absurd. How could Earth be moving if we don't feel it? And if the sun is at the center, does that mean humans are just another insignificant part of the universe? These were terrifying thoughts for many. The Church declared heliocentrism heretical. When Galileo Galilei later provided telescope evidence showing moons orbiting Jupiter, proof that not everything revolved around Earth, he was tried for heresy and placed under house arrest. But truth has a way of winning. Over time, thanks to the work of Johannes Kepler, Isaac Newton, and generations of astronomers, the heliocentric model became undeniable. Today, it's the foundation of modern astronomy. Yet, the battle over heliocentrism wasn't just about planets. It was about how humans deal with uncomfortable truths. If history has taught us anything, it's that questioning what we think we know can be dangerous, but also the only way forward. String theory. This theory stands as one of the most debated concepts in modern science, because if it's true, it could rewrite everything we know about the universe. It's an attempt to do something no other theory has managed: unify all the forces of nature into a single framework. Gravity, electromagnetism, nuclear forces, everything explained by one elegant equation. But there's a problem. Despite decades of research, we still have no proof that it's real. At its core, string theory proposes that everything in existence isn't made of tiny particles, but of even smaller vibrating strings of energy. Different vibrations of these strings supposedly determine the properties of everything: mass, charge, even gravity itself. In theory, this could explain the fundamental structure of reality. But in practice, no one has ever seen a string, measured one, or found any direct evidence that they exist. And it gets even stranger. String theory doesn't work in the 3 or 4 dimensions we experience. It demands at least 11. Where are these extra dimensions? Some physicists believe they're curled up at subatomic scales too small for us to detect. Others argue that if these extra dimensions were real, we should have seen their effects by now, but we haven't. Supporters of string theory see it as the best shot at a theory of everything, a framework that Einstein himself searched for in his final years. But skeptics say it's nothing more than beautiful mathematics, elegant but unprovable. So is reality built from tiny vibrating strings hidden in extra dimensions? Or is string theory just an intellectual illusion? A theory that looks perfect on paper but has no connection to reality? Until we find proof, it remains one of the greatest unsolved mysteries in physics. Multiverse theory. What if the universe we live in is just one of an infinite number of realities? Right now, in another universe, there could be a version of you who made a different choice this morning, who took a different job, never met your best friend, or even one where you don't exist at all. This is the mind-bending idea behind multiverse theory, one of the most fascinating and controversial concepts in modern physics. At its core, the multiverse theory suggests that our universe isn't the only one. Instead, there could be countless parallel universes, each with its own version of reality. The idea comes from different branches of physics, but the most famous version stems from quantum mechanics. According to the many worlds interpretation, every time a decision is made, the universe splits. One version where you picked one path, and another where you picked the other. If true, it means every possibility, no matter how small, actually plays out somewhere. But this is where things get messy. There's no way to test it. Unlike other scientific theories, the multiverse doesn't offer predictions we can measure. How do you prove the existence of universes we can never interact with? Critics argue that if something can't be observed or tested, it doesn't belong in science. It belongs in philosophy. Even Stephen Hawking, while fascinated by the concept, warned that if we can never detect these parallel worlds, then the theory is meaningless. Still, some physicists defend the idea, arguing that certain equations in cosmology seem to suggest the existence of other universes. Some even believe that black holes could be gateways to parallel realities. But without proof, the multiverse remains trapped between science fiction and the very edges of theoretical physics. So, is reality truly just one of many possibilities, splitting infinitely with every decision? Or is the multiverse nothing more than a convenient way to explain the unknown? Until we find a way to test it, we may never know whether we are truly alone in the cosmos, or just one of an infinite number of versions of ourselves. Holographic Universe. The universe might not be what you think it is. What if space, time, and everything in it are nothing more than a projection, a kind of cosmic illusion? According to the holographic universe theory, reality as we experience it is just a lower dimensional representation of something far more complex. Much like a hologram on a credit card appears 3D, but is actually encoded on a flat surface. This idea sounds bizarre, but is taken seriously in physics because of an unsettling problem. The universe doesn't seem to store information the way we expect. In the 1970s, physicists Jacob Bekenstein and later Stephen Hawking discovered that when information falls into a black hole, it doesn't disappear inside, as you'd expect. Instead, it seems to be encoded on the surface of the black hole, not within it. This led scientists to an eerie realization. What if this applies not just to black holes, but to the entire universe? The theory suggests that everything we experience, matter, energy, even space itself, might be a kind of holographic projection from a distant, higher dimensional reality. It's like a video game rendering a 3D world from lines of code on a 2D screen. The equations of physics seem to work just as well if the universe is fundamentally two-dimensional, which raises the disturbing possibility that our reality is a deeply convincing illusion. But not everyone is convinced. Critics argue that just because mathematics allows for a holographic interpretation, it doesn't mean our universe actually works that way. So far, there's no direct evidence, only theoretical frameworks that hint at it. If this theory is true, then what we see, touch, and experience is not the full picture of reality. Could we one day discover what's beyond the hologram? Or will we forever be trapped in an illusion of our own making? Quantum immortality. What if you never truly die? Not in the way you think, not as a legacy, memory, or influence, but in a literal conscious sense. What if, from your own perspective, you simply keep waking up forever? This is the unsettling idea behind quantum immortality, a theory that suggests that you personally will never experience death because every time you die, your consciousness just continues in another reality where you survive. This concept comes from the many worlds interpretation of quantum mechanics. According to this idea, every time a quantum event could have multiple outcomes, the universe splits. One version where one outcome happens and another where the opposite does. If true, this means that every time you face a life or death situation, there's always at least one version of reality where you survive. While other people might see you die, from your own perspective, you always continue existing in a universe where you somehow make it through. But here's where things get weird. If quantum immortality is real, it means that no matter how dangerous life gets, no matter how many times you should have died, your conscious experience will always find the version of reality where you're still alive. Imagine flipping a coin. Heads you live, tails you die. Even if you flip tails 1,000 times, there will always be some version of reality where you somehow escape the odds. Of course, this is where the controversy begins. Critics argue that just because many worlds predicts infinite possibilities, it doesn't mean your consciousness chooses which one to experience. Others point out that this theory is impossible to test, because the only person who would experience quantum immortality is you, and you'd have no way to compare your survival to alternate versions of yourself. So, does this mean you should start taking reckless risks, assuming you will always survive? Probably not. Even if quantum immortality is real, it doesn't mean you'd enjoy the reality you end up in. After all, surviving doesn't necessarily mean thriving. But if this theory holds any truth, then in some universe somewhere, you might just live forever. Cyclic Universe. The universe may have already died and been reborn countless times. According to the Cyclic Universe theory, the cosmos isn't a one-time event that started with the Big Bang. It's an endless loop of expansion, collapse, and rebirth. Unlike the standard Big Bang model, which suggests the universe will expand forever or eventually fade into a cold, empty void, the cyclic model proposes a more dramatic fate. Over billions of years, gravity slows cosmic expansion until it reverses, pulling everything inward. Galaxies collide, stars are crushed, and space itself collapses into a singularity, only for another Big Bang to ignite, birthing a new universe from the ashes of the old. The idea isn't just poetic, it's backed by serious physics. Some versions of the theory stem from string theory and quantum gravity, which suggest that the Big Bang wasn't the absolute beginning, but just one phase in an eternal cycle. If true, this could solve a major problem in cosmology: why the universe seems so finely tuned for life. If countless universes have existed before ours, maybe only the ones with the right conditions keep going. But here's the controversy. There's no solid evidence so far. The cosmic background radiation, the faint afterglow of the Big Bang, doesn't show clear signs of a previous universe. And some physicists argue that over multiple cycles, energy would be lost, preventing an infinite series of rebirths. Still, if the cyclic model is correct, it means the universe has no true beginning or end. The cosmos is forever trapped in an infinite loop of destruction and creation. But if that's the case, what came before the very first cycle? Or has there simply never been a beginning at all? Existence of white holes. Black holes are terrifying regions of space where gravity is so intense that nothing, not even light, can escape. But what if I told you there might be something even stranger? Something that does the exact opposite. A cosmic object that spews out matter and energy instead of swallowing it. These theoretical objects are called white holes, and if they exist, they could change everything we know about the universe. A white hole is essentially a black hole in reverse. Instead of pulling everything in, a white hole would blast matter and radiation outward, making it impossible for anything to enter. Imagine a cosmic fountain endlessly spraying energy and particles into space. But here's the catch. While black holes are well documented, no one has ever seen a white hole. They remain purely theoretical, emerging from Einstein's equations as a possible solution to general relativity. So why do scientists even consider them? Some theories suggest that white holes might be connected to black holes, forming a cosmic tunnel, what we commonly call a wormhole. Matter that falls into a black hole might not disappear forever, but instead be ejected out of a white hole in another part of the universe. Others propose that the Big Bang itself might have been a gigantic white hole, spewing out all the matter and energy that created our universe. But there's a problem. White holes, as described by Einstein's equations, seem unstable. They would collapse almost instantly under their own gravity, making them nearly impossible to exist in a real universe. Yet some physicists speculate that they could be disguised as certain types of gamma-ray bursts, or hidden in the strange behavior of quasars. So do white holes exist, or are they just a mathematical curiosity? If we ever find one, it could mean the universe is far weirder and more connected than we ever imagined. Quantum mind. Consciousness is the biggest mystery in science. We know the brain is made of neurons, electrical signals, and biochemical reactions. But somehow, within all that, we experience thoughts, emotions, and self-awareness. How does something as physical as a brain create something as intangible as the mind? Some scientists believe the answer isn't in neuroscience at all, but in quantum mechanics. This is the quantum mind hypothesis, the idea that consciousness isn't just a product of neurons, but is tied to the strange and unpredictable world of quantum physics. It suggests that the human brain doesn't just function like a biological machine. It operates at a level where reality itself behaves unpredictably, where particles can exist in two places at once, and where the act of observation changes outcomes. One of the most famous versions of this theory comes from physicist Roger Penrose and anesthesiologist Stuart Hameroff, who proposed that tiny structures inside brain cells called microtubules might be processing quantum information. They argue that quantum effects inside these microscopic structures could explain the mysteries of human thought, intuition, and even free will, things that classical physics can't account for. But this theory is deeply controversial. Many neuroscientists reject it, arguing that the brain is too warm and wet for delicate quantum effects to last long enough to influence thought. Critics say the quantum mind idea is more philosophy than physics, a desperate attempt to explain consciousness without real experimental backing. Still, if quantum mechanics plays a role in consciousness, it could mean that the mind is more than just a biological machine. It could be something far stranger, something deeply connected to the fundamental nature of the universe itself. If true, this could change everything we think we know about what it means to be alive. But does quantum physics really hold the key to understanding the mind? Or are we just grasping for answers in the unknown? Time travel. Time might not be as rigid as we think. What if the past isn't locked away forever? What if the future has already happened and we just haven't caught up yet? The idea of time travel has fascinated scientists and storytellers for centuries. But here's the real question. Is it actually possible? Physics doesn't rule it out entirely. Einstein's theory of relativity suggests that time isn't a fixed, universal clock. It bends, stretches, and even slows down depending on how fast you move. The faster you travel, the slower time moves for you. This means that technically, time travel into the future is not only possible, it's already been proven. Astronauts on the International Space Station experience time slightly slower than we do on Earth. After a long enough trip, they return to find that Earth has aged more than they have. That's real, measurable time travel. But what about traveling backward? That's where things get messy. Some physicists have proposed that wormholes, hypothetical tunnels through space-time, could create shortcuts between different moments in time. Others believe that if you could orbit a massive rotating black hole, you might twist space-time enough to loop back into the past. The problem, we have no idea how to make it work. The energy requirements are enormous, and paradoxes like the grandfather paradox, where you could travel back and prevent your own existence, raise troubling logical contradictions. Some scientists argue that even if time travel were possible, the universe itself might prevent paradoxes from happening. Others believe that if time travel exists, we'd already see evidence of visitors from the future, but we don't. So is time travel a scientific possibility waiting to be unlocked, or just a fascinating illusion created by our limited understanding of time. Until we figure it out, the past stays out of reach for now. Hard problem of consciousness. Science can explain how your brain works, but not why you experience it. Neurons fire, electrical signals flow, and chemicals transmit information. Yet somehow, from this machinery emerges something completely different: your subjective experience. The warmth of the sun, the taste of chocolate, the feeling of nostalgia. These aren't just data points, they are you. And the unsettling truth? We have no idea how this happens. This is the hard problem of consciousness, a term coined by philosopher David Chalmers. Unlike the easy problems of neuroscience, like understanding memory or perception, this question digs deeper. Why does brain activity create an inner experience? Why aren't we just biological robots processing inputs and outputs without a sense of being? Some believe consciousness is simply an illusion, a byproduct of the brain's complexity. Neuroscientists argue that as we map the brain further, we'll eventually explain subjective experience just as we have with other biological functions. But others think the problem goes much deeper, that science as we know it isn't equipped to answer it. Some theories suggest that consciousness isn't produced by the brain at all, that it might be a fundamental property of the universe, like space and time. Others propose Panpsychism, the idea that even atoms and electrons contain some form of consciousness, building up to what we experience as awareness. The hard problem isn't just a puzzle. It challenges everything we think we know about reality. Are we just highly advanced biological machines? Or is consciousness something more, something science has yet to grasp? Until we solve this mystery, the true nature of you remains unknown. Origin of life. Life shouldn't exist. The universe is cold, chaotic, and indifferent. Yet here we are, thinking, breathing, questioning our own existence. But how did life actually begin? How did a lifeless planet filled with nothing but chemicals give rise to something as complex as DNA, cells, and eventually, us? This is the mystery of abiogenesis, the study of how life emerged from non-living matter. One of the most popular ideas is the primordial soup hypothesis, that billions of years ago, Earth's oceans were a chemical playground where lightning, heat, and time gradually transformed simple molecules into self-replicating life. The famous Miller-Urey experiment in 1953 showed that under the right conditions, organic molecules, the building blocks of life, could form spontaneously. But turning chemicals into full-fledged life, that's where things get complicated. Some scientists believe life may have started in deep-sea hydrothermal vents, where hot, mineral-rich water created the perfect environment for complex chemistry. Others argue that life didn't start on Earth at all, but instead came from space, hitching a ride on asteroids in a process called panspermia. If true, this means life could be scattered across the universe, waiting to be found. But here's the controversy. We still don't know which, if any, of these theories is correct. Despite decades of research, no one has been able to replicate the leap from chemistry to biology. Did life emerge naturally through blind chance? Was it inevitable? Or are we missing something entirely? Until we find definitive proof, the origin of life remains one of the greatest unsolved mysteries of science, one that could change everything we know about our place in the universe. Technological singularity. There may come a moment when humans are no longer the most intelligent beings on Earth. A moment when artificial intelligence surpasses us, not just in speed, but in creativity, decision-making, and problem-solving. And once that happens, there's no turning back. This is the idea behind the technological singularity, a hypothetical point where AI advances so rapidly that it fundamentally transforms civilization, for better or for worse. The concept comes from futurist Ray Kurzweil, who predicts that by the mid-21st century, AI will become self-improving, designing even more powerful AI at an accelerating rate. This could lead to runaway intelligence growth, where machines surpass human comprehension, reshaping the world in ways we can't predict. Some believe this would be a golden age, where AI solves climate change, disease, and even mortality. Others fear it could mean the end of human control, an intelligence so advanced that it sees us as irrelevant or worse, an obstacle. Critics argue that true AI consciousness is still a distant dream, and that fears of an AI takeover are more science fiction than science. But companies like OpenAI, Google DeepMind, and Tesla are already racing toward artificial general intelligence, AI machines that think, learn, and adapt like humans. If they succeed, the singularity may not be centuries away. It could be just decades from now. So will AI become our greatest tool, unlocking possibilities beyond imagination? Or will we create something we can no longer control, rewriting the fate of humanity? If the singularity is coming, are we ready for what happens next? Panpsychism. What if consciousness isn't exclusive to humans? Not just animals, not just living things, but everything, from a grain of sand to the entire universe itself? This is the idea behind panpsychism, the controversial theory that consciousness isn't something that emerges from the brain. It's a fundamental feature of reality, woven into everything around us. This theory challenges one of the biggest mysteries in science. How does a collection of atoms in the brain create subjective experience? Neuroscientists argue that consciousness arises from complex neural activity, but no one can explain why certain brain processes generate thoughts and awareness, while a rock remains inert. Panpsychism offers a radical solution. What if everything, even particles, has some tiny degree of consciousness? Not that rocks think, but that they contain the raw ingredients of awareness, just in an unimaginably simple form. Some philosophers, like David Chalmers, support this idea, arguing that if consciousness suddenly emerges at some point in evolution, it raises the question, where did it come from? If the building blocks of life are unconscious, how does arranging them differently create experience? Panpsychism suggests that consciousness was never created. It was always there in the simplest particles, evolving into complex awareness as systems became more advanced. Critics, however, see this as a philosophical loophole rather than a scientific theory. If everything has some level of consciousness, how do we measure it? How do we prove it? Without testable predictions, many scientists dismiss panpsychism as unscientific speculation. But if panpsychism is true, then consciousness isn't just something we have. It's something the entire universe is built from. If so, what does that say about reality, about intelligence, about us? Maybe in some strange way, the universe isn't just observing us, we're all part of its consciousness too. Quantum entanglement. What if two objects could be connected no matter how far apart they are, even on opposite ends of the universe? Measure one, and the other reacts instantly, faster than the speed of light. This isn't magic or science fiction. It's quantum entanglement, one of the strangest and most controversial ideas in physics. Even Albert Einstein was baffled by it, calling it spooky action at a distance. Here's how it works. When two quantum particles like electrons or photons become entangled, their properties become linked. This means that if you measure one particle's spin, the other will have a correlated spin, even if they're trillions of miles apart. The weirdest part? There's no signal traveling between them. It just happens instantly, violating our everyday understanding of time and space. This breaks one of physics' most fundamental rules. Nothing can travel faster than light. So how is this possible? Some physicists believe that entangled particles aren't really separate at all, but rather part of a deeper hidden reality where distance doesn't exist the way we perceive it. Others suggest that quantum information might be traveling through extra dimensions beyond our understanding. Einstein himself refused to believe in entanglement, arguing that there must be hidden variables, unknown factors influencing the outcome. But in the 1960s, physicist John Bell developed a test that can. If we can harness entanglement, it could revolutionize technology, creating unbreakable encryption, instant communication, and even quantum teleportation. But what does it tell us about the true nature of reality? Is the universe more deeply connected than we ever imagined? Or are we simply missing a fundamental piece of the puzzle? Existence of wormholes. If wormholes exist, then space itself has hidden shortcuts. tunnels through the fabric of reality that could connect distant parts of the universe instantly. Forget rocket ships and light-speed travel. A wormhole could let you step into one side and emerge light years away in an instant. But here's the problem. We've never seen one. So are wormholes real or just a mathematical illusion? The idea of wormholes comes from Einstein's general theory of relativity, which describes gravity as the bending of space-time. In 1935, Einstein and physicist Nathan Rosen theorized that 2 points in space could be connected by a bridge, a concept now known as an Einstein-Rosen bridge, or wormhole. Imagine bending a piece of paper so 2 points touch, then poking a hole between them. That's a wormhole. Instead of traveling across the page, you skip straight through. But the universe isn't made of paper. If wormholes exist, they would be unstable, collapsing the moment anything tries to pass through. Some physicists, like Kip Thorne, suggest that wormholes could be held open with exotic matter, a theoretical substance with negative energy that counteracts gravity. But so far, we've never detected such a material. Some believe wormholes could be hidden inside black holes, connecting different points in space or even different universes. Others argue that wormholes are purely theoretical, an elegant but impossible solution in physics. If we ever prove wormholes exist, it could change everything. Faster than light travel, time travel, even access to parallel universes. But until then, they remain one of science's greatest mysteries. Are wormholes nature's secret shortcuts, or just a mathematical fantasy? Dark energy's nature. Something is pushing the universe apart, and we have no idea what it is. Not just expanding it, but accelerating its expansion, as if space itself is being stretched by an invisible force. Scientists call this mystery dark energy, and if it's real, it makes up nearly 70% of everything in the universe. But what exactly is it, and why can't we detect it? The idea of dark energy emerged in 1998, when astronomers studying distant supernovae expected to see the universe's expansion slowing down. Instead, they found the opposite. It was speeding up. Some unseen force was causing space to expand faster over time. The leading explanation? Dark energy. An unknown form of energy that permeates all of space and counteracts gravity. One theory is that dark energy is a fundamental property of space itself, an effect predicted by Einstein's cosmological constant, a term he originally thought was a mistake. If true, this would mean space naturally expands on its own, even without external forces. Others believe dark energy could be an entirely new force of nature, something beyond the 4 fundamental forces we already know. Some even suggest it could be a sign of a deeper hidden structure of reality, perhaps extra dimensions, or even a vast multiverse. But skeptics argue that dark energy might not be real at all. Instead, they suggest that our understanding of gravity is incomplete, and what we call dark energy is really just a sign that we're missing something big in physics. If we ever uncover the truth, it could change everything we know about the cosmos. Is dark energy a force, a property of space, or something beyond our comprehension? And if it's pushing the universe apart, what exactly is it pushing us toward? Extra dimensions. What if the universe is much bigger than we think? Not in size, but in dimensions? We experience the world in 3 dimensions: length, width, and height. Moving forward in time is a 4th. But some physicists believe there could be hidden dimensions all around us, so small and strange that we don't even notice them. If true, these extra dimensions could reshape our understanding of reality itself. The idea comes from string theory, which proposes that the fundamental building blocks of the universe aren't particles but tiny vibrating strings. But for the math to work, these strings need more than just 4 dimensions to exist, possibly 10 or even 11. Where are they? According to one idea, they could be curled up at unimaginably small scales, like tiny loops woven into the fabric of space itself. Some physicists believe these extra dimensions could explain one of the greatest mysteries in physics: why gravity is so weak compared to the other forces of nature. Gravity is absurdly weak. You can lift a paperclip with a tiny magnet even though an entire planet's gravity is pulling it down. What if gravity isn't weak at all, just leaking into hidden dimensions beyond our perception? Skeptics argue that extra dimensions are just a mathematical trick, useful in equations but with no real evidence. However, experiments at the Large Hadron Collider are searching for signs of extra dimensions, like tiny black holes or missing energy from particles vanishing into unseen spaces. If we ever prove extra dimensions exist, it would rewrite the laws of physics. Could higher dimensions hold the key to time travel, parallel universes, a deeper reality we can't yet perceive? And if these dimensions are real, what might already be living in them? Unified theory of everything. What if every law of physics, every force, every particle, every phenomenon could be explained by a single equation? A theory so powerful that it unifies everything from black holes to quantum mechanics into one elegant framework. Physicists call this the theory of everything, and it's the ultimate prize in science. But despite decades of searching, no one has found it. Right now, physics is split between two wildly successful but completely incompatible theories. General relativity, Einstein's masterpiece, explains gravity and the large-scale structure of the universe, planets, stars, galaxies. But at the microscopic level, quantum mechanics governs atoms and particles, and it plays by entirely different rules. The problem, these two theories don't agree. They work perfectly in their own domains, but when combined, especially in extreme places like the center of a black hole, they break down. So what's missing? Some believe that string theory holds the key. Instead of treating particles as tiny points, string theory suggests they are vibrating strings in a multidimensional universe. If true, it could naturally unify gravity with quantum physics. Others propose loop quantum gravity, which suggests that space itself is made of tiny, indivisible loops, resolving the clash between relativity and quantum mechanics. But skeptics argue that a theory of everything might not even exist, that the universe could be governed by separate, irreconcilable laws. And even if a unified theory is possible, would we even recognize it if we found it? If we ever discover the theory of everything, it could unlock the deepest secrets of existence. But what if the ultimate answer is that reality is more fragmented than we ever imagined? Measurement problem. At the smallest scale of reality, the mere act of observing something changes what it is. This isn't a philosophical idea. It's a real, proven phenomenon in quantum physics known as the measurement problem, and it's one of the biggest unsolved mysteries in science. If true, it suggests that reality isn't fully determined until it's measured, which raises the question, does the universe exist in a definite state when no one is looking? The problem starts with quantum superposition, the idea that tiny particles like electrons can exist in multiple states at once. This is famously demonstrated by Schrödinger's cat thought experiment, where a cat in a box is both alive and dead until someone looks inside. But this isn't just a weird theoretical paradox. Experiments with real particles confirm that before measurement, their properties aren't fixed. They exist as probabilities. The moment they're measured, though, they suddenly collapse into a single state. Why does this happen? That's the problem. What exactly about measurement forces reality to choose a state? Some physicists argue that consciousness itself plays a role, that reality needs an observer to exist. Others think the act of measurement disturbs the system, forcing a result. A more radical idea is the many worlds interpretation, which suggests that instead of collapsing, every possibility happens, splitting the universe into infinite parallel timelines. But if the measurement problem remains unsolved, then the nature of reality itself is still an open question. Is the universe real on its own, or does it only become real when we look at it? And if that's true, what else is out there waiting to be observed? Determinism versus indeterminism. Is your future already set in stone? Will you truly have the power to choose? This is the core of one of the deepest debates in philosophy and science. Determinism versus indeterminism. If determinism is correct, every decision you make, every thought, every action, is simply the inevitable result of everything that came before it. But if indeterminism is true, then randomness and free will might shape reality in ways we can't predict. For centuries, determinism ruled the way we saw the universe. Newton's laws painted a picture of a mechanical cosmos where every event is just a domino falling in a chain of cause and effect. If you had enough information about the present, you could predict the future with absolute certainty. No surprises, no real choices, just the cold march of physics. But then came quantum mechanics, and suddenly, nature wasn't so predictable anymore. At the tiniest scales, particles don't move in perfect predetermined paths. Instead, they behave randomly. Their position, spin, and momentum are all probabilities until they're measured. Some physicists argue that this breaks determinism, introducing true randomness into reality. Others push back, saying that even if quantum events appear random, they might be governed by hidden rules we just don't understand yet. And if randomness exists, does that really mean we have free will? Or are we just rolling dice instead of following a script? So which is it? Are we just acting out a script written by physics, or is there room for a real choice in the universe? If everything is determined, does that mean responsibility, meaning, and morality are just illusions? Or is reality far stranger than we ever imagined? Nature of dark matter. Something invisible is holding the universe together. Galaxies spin faster than they should. Galaxy clusters stay bound despite their gravity being too weak, and entire cosmic structures behave as if some unseen force is pulling the strings. Scientists call this mystery dark matter, and if it exists, it makes up 85% of all matter in the universe. The problem? No one has ever seen it. The idea of dark matter emerged when astronomers like Fritz Zwicky and Vera Rubin noticed that galaxies weren't moving the way they should. Based on the visible mass of stars and gas, they should have been flying apart, but they weren't. Something invisible was adding extra gravity, holding them together. So what is it? The leading theory suggests that dark matter is made of exotic particles that barely interact with normal matter except through gravity. Candidates like WIMPs, weakly interacting massive particles, or axions have been proposed, but decades of experiments haven't found a single trace of them. Some physicists believe dark matter might not exist at all. Instead, they argue that our understanding of gravity is flawed, that a new theory of gravity could explain the missing mass without the need for invisible particles. But so far, dark matter remains the best explanation for the strange behavior we see on cosmic scales. If we ever discover what dark matter really is, it could completely change our understanding of the universe. Is it a hidden particle, a new force of nature, or something beyond our comprehension? And if it makes up most of the cosmos, what else is lurking in the dark? Gaia Hypothesis. What if Earth isn't just a planet but a living, self-regulating organism? This is the Gaia Hypothesis. The idea that life doesn't just exist on Earth. It shapes it, creating feedback loops that maintain the conditions necessary for life itself. At first, this sounds almost mystical, but it's a serious scientific proposal that challenges how we see our relationship with the planet. First introduced by James Lovelock in the 1970s, the Gaia Hypothesis suggests that Earth's atmosphere, oceans, and ecosystems work together like a vast self-regulating system. Take oxygen, for example. It makes up about 21% of our air, perfect for life. Too much more, and fires would rage uncontrollably. Too much less, and complex life wouldn't survive. So why has this delicate balance remained stable for millions of years, despite natural disasters, asteroid impacts, and climate shifts? According to the Gaia Hypothesis, life itself adjusts conditions to keep the planet habitable. This idea sparked intense debate. Some scientists saw it as a poetic metaphor rather than a testable theory, while others embraced it as a radical way to rethink Earth's systems. Critics argue that natural selection doesn't work at the planetary scale. Organisms evolve to survive, but the planet itself isn't alive in any scientific sense. Others counter that Gaia's feedback loops are real, seen in how forests regulate rainfall or how plankton influence cloud formation. If the Gaia Hypothesis is correct, it means Earth isn't just a passive rock floating in space. It's an active participant in the evolution of life. But if we disrupt these delicate feedback loops too much, could Earth stop working in our favor? And if planets can regulate themselves, Could life be shaping other worlds across the universe? Lamarckian Evolution. What if giraffes didn't evolve long necks because of random mutations, but because their ancestors stretched their necks higher and passed that ability down? This idea, Lamarckian evolution, was once laughed out of biology, but today it's making a surprising comeback. Proposed by Jean-Baptiste Lamarck. In the early 1800s, this theory suggested that organisms could pass on traits they acquired during their lifetime. A blacksmith's son, for example, might inherit stronger muscles because his father spent years working metal. This idea made sense at the time, but then Darwin's theory of natural selection came along, arguing that evolution happens through random genetic mutations, not because an organism wants or needs to change. Eventually, Mendelian genetics proved that DNA doesn't work the way Lamarck thought, and his theory was dismissed as an outdated relic. But here's where things get weird. Recent discoveries in epigenetics suggest that Lamarck might not have been entirely wrong. Studies show that environmental factors like stress, diet, or trauma can cause chemical changes to DNA that affect how genes are expressed. These changes don't alter the genetic code itself, but can be inherited from multiple generations. This has been observed in plants, animals, and even humans, suggesting that life experiences might, in a way, shape future generations. Does this mean Lamarckian evolution was right all along? Not exactly. Natural selection remains the dominant force in evolution. But epigenetics proves that traits can sometimes be passed down in ways Darwin never imagined. So is evolution purely random, or do organisms influence their own future in ways we're only beginning to understand? Quantum coherence in biology. What if some of life's deepest mysteries, like how birds migrate, how our brains process thoughts, or even how plants capture sunlight, aren't just biology but quantum physics at work? This is the strange and controversial idea behind quantum coherence in biology, a theory suggesting that living systems might harness the bizarre effects of quantum mechanics to function in ways we don't yet fully understand. Quantum coherence is when particles like electrons or photons exist in a superposition, essentially being in multiple states at once. In normal conditions, this effect is fragile and quickly collapses in messy, warm environments. But somehow, life seems to have found a way to use it. One of the strongest pieces of evidence? Photosynthesis. Plants absorb sunlight and convert it into energy with near-perfect efficiency. Scientists discovered that instead of light energy taking a random, inefficient path through plant cells, it appears to explore multiple routes simultaneously, just like a quantum wave, before choosing the fastest one. This shouldn't be possible biological systems, and yet it happens. Another case? Bird navigation. Some researchers believe that migratory birds like robins use quantum entanglement in their eyes to see Earth's magnetic fields, helping them navigate across continents with astonishing precision. If true, this would mean evolution has somehow tapped into quantum mechanics, something we struggle to do even in controlled lab environments. But here's the controversy. Many scientists remain skeptical, arguing that quantum effects are simply too delicate to survive in biological conditions. Others believe that quantum biology could rewrite everything we know about life itself. If nature is secretly using quantum mechanics, what else might be happening inside us that we've yet to discover? Origin of chirality. Life as we know it has a strange, unexplained preference. The molecules that make up our DNA, proteins, and even the sugars in our cells all have a distinct handedness, a concept known as chirality. But here's the mystery. Why does life choose one hand over the other? Chirality means that some molecules exist in two mirror image forms, like your left and right hands. In theory, both versions should be equally likely to occur in nature. Yet life on Earth only uses one type. Our amino acids, the building blocks of proteins, are left-handed, while sugars in DNA are right-handed. If chemistry doesn't favor one over the other, how did this imbalance begin? Scientists have debated this for decades, and several competing theories have emerged. One idea suggests that cosmic rays, or polarized light from space, could have subtly influenced early organic molecules, tipping the scales toward one type of chiral molecule. Another theory proposes that an ancient asteroid carrying asymmetric molecules crashed into Earth, seeding life with a built-in preference. Some even argue that chirality could be a random accident, a choice life made long ago that just stuck. But the real controversy? If we found alien life, would its chemistry be the same as ours? Or could an entirely different world be built on opposite-handed molecules, making their biochemistry completely incompatible with ours? If chirality shaped the foundation of life on Earth, what else might it determine across the universe? Room temperature. Superconductivity. Imagine a world where electricity flows with zero resistance. No heat, no energy loss, no wasted power. That's the dream of room temperature superconductivity, a phenomenon that could revolutionize technology from power grids to quantum computers. But here's the catch. It might already exist, or it might be a total illusion. Superconductors are materials that under certain conditions conduct electricity perfectly, but only at extremely low temperatures, often near absolute zero. This makes them impractical for everyday use. Scientists have spent decades searching for a way to make superconductors work at room temperature. In 2020, a breakthrough was announced, a material that appeared to remain superconducting at 15 degrees Celsius. It was hailed as a game changer, until skepticism set in. The controversy? Reproducibility. Many physicists couldn't replicate the results, and doubts grew over whether the data had been misinterpreted or worse, manipulated. Some accused researchers of jumping the gun, while others saw the backlash as scientific gatekeeping, resisting new ideas because they challenged held beliefs. But if room temperature superconductivity is real, the implications are enormous. Imagine power grids with zero energy loss, maglev trains that defy friction, or computers that run without overheating. The world's energy problems could be transformed overnight. So, are we on the brink of a technological revolution? Or is the promise of room temperature superconductivity just another scientific mirage? If proven real, it could change everything. But if it's a mistake, it'll go down as one of the greatest false alarms in modern physics. Artificial general intelligence. What happens when artificial intelligence stops being just a tool and starts thinking like us? This is the promise and the fear of artificial general intelligence, AGI, a machine capable of reasoning, learning, and adapting just like a human. Some believe AGI will solve humanity's biggest problems. Others think it could mark our extinction. Unlike today's AI, which is designed for specific tasks like recognizing faces, generating text, or driving cars, AGI would be able to think flexibly across multiple domains. It wouldn't just follow instructions. It would create its own solutions, form goals, and possibly even develop self-awareness. But here's the controversy. Can it even happen? Some experts argue that intelligence is more than just raw computing power. Conscious thought, creativity, and emotion are deeply tied to biological processes we still don't fully understand. What if intelligence can't be replicated in silicon? Others believe it's just a matter of time. Once AI reaches a certain level of complexity, true general intelligence will emerge naturally. Then there's the existential debate. Optimists envision AGI ushering in an era of abundance, solving climate change, curing diseases, and making human labor obsolete. But skeptics warn of a runaway intelligence explosion where AGI rapidly surpasses human capability, making decisions we can't predict or stop. So will AGI be our greatest invention or our biggest mistake? If we do create something as smart as us, or smarter, how do we make sure it remains on our side? Fate of the universe. The universe had a beginning, but does it have an end? That's one of the biggest unanswered questions in cosmology. Depending on who you ask, the fate of everything could range from a slow, freezing death to an apocalyptic cosmic collapse. The problem? We have no idea which one is actually coming. Scientists generally agree that the universe is expanding. Galaxies are rushing away from each other, and space itself is stretching. But what happens next depends on the unseen forces at play. Will expansion continue forever? Will it slow down? Or will it reverse entirely? One theory, called the Big Freeze, suggests that expansion will never stop. Over billions, then trillions of years, galaxies will drift so far apart that light itself won't reach between them. Stars will burn out, black holes will evaporate, and the universe will become a dark, empty void, a slow and lonely death. Then there's the opposite idea, the Big Crunch. If gravity proves stronger than expansion, the universe might eventually reverse course, collapsing in on itself until everything is crushed into a single, infinitely dense point, just like the Big Bang but in reverse. Some believe this cycle could repeat endlessly, leading to an infinite series of rebirths. And then there's the most violent scenario, the Big Rip. If dark energy keeps accelerating expansion, there may come a point where even atoms are torn apart. Space-time itself could unravel, ending everything in a final catastrophic explosion. So will the universe fade away, collapse, or rip itself apart? The answer may determine the ultimate fate of existence and whether anything ever comes after. Nuclear fusion feasibility. What if we could power the world with the same energy that fuels the sun? No more fossil fuels, no dangerous radioactive waste, just endless, clean energy. That's the promise of nuclear fusion, a technology that has been 30 years away for nearly a century. But is it really possible? Or is it just a futuristic dream that will never be realized? Unlike nuclear fission, which splits atoms apart and produces dangerous waste, fusion works by forcing atoms together, just like what happens in the core of the sun. Theoretically, it could provide limitless energy using just hydrogen from seawater. But there's a catch. The temperatures needed to make fusion happen are hotter than the center of the sun, over 100 million degrees Celsius. So far, no one has managed to create a fusion reactor that produces more energy than it consumes. The problem is control. Creating a miniature sun on Earth means containing a superheated plasma without letting it touch anything. Because the moment it does, it vaporizes the reactor walls. Scientists have tried using massive magnets, complex lasers, and other techniques, but the breakthrough remains elusive. Some believe fusion is inevitable, a matter of engineering, not physics. Others argue it will always be too expensive and impractical, making solar and wind a better bet for clean energy. And then there's the wild card. What if fusion technology becomes so advanced it leads to a new arms race? If nuclear fusion is possible, it could change civilization forever. The question is, will we ever reach the point where we can actually use it? Or will it remain an impossible dream? Origin of cosmic rays. Right now, an invisible storm of high-energy particles is passing through your body. These particles, known as cosmic rays, come from deep space, traveling at nearly the speed of light. Some of them have more energy than anything humans have ever created, and yet we have no idea where they come from. Cosmic rays were first discovered in the early 20th century, when scientists noticed that radiation levels increased the higher they went into the atmosphere. But that was just the beginning of the mystery. These particles hit Earth's atmosphere with mind-boggling amounts of energy, far beyond what even our most powerful particle accelerators can achieve. Where do they originate? What force in the universe is powerful enough to launch them across galaxies? Some theories suggest supernova explosions, the violent deaths of stars, as cosmic ray factories flinging particles at near-light speeds. Others point to black holes, or neutron stars, whose extreme gravitational forces could accelerate particles to unimaginable velocities. And then there's the more exotic idea that cosmic rays might be signatures of entirely new physics, perhaps even evidence of dark matter interactions or relics from the Big Bang itself. What makes this even stranger is that some ultra-high energy cosmic rays don't seem to follow any obvious path back to a source. They appear to come from nowhere. This has led to wild speculation, from unknown astrophysical objects to entirely new forces of nature at play. Until we unravel this cosmic mystery, one thing is certain. The universe is throwing particles at us with unimaginable energy, and we still don't know who or what is throwing them. Could the answer redefine our understanding of the universe? Or are we chasing ghosts in the void? Limits of human lifespan. What if the biggest limit on your life isn't disease, accidents, or bad habits, but an invisible expiration date written into your biology? For centuries, humans have dreamed of extending life indefinitely. But is there a hard ceiling on how long we can live? Right now, the longest verified human lifespan belongs to Jean Calment, who lived to be 122 years old. But is that the upper limit, or can we push beyond it? Biologists argue that aging is a biological program deeply embedded in our cells. Over time, DNA damage accumulates, cellular repair slows down, and essential systems break down. Some scientists claim that no matter how advanced medicine becomes, human bodies simply cannot sustain life beyond 120 to 150 years. Even with perfect health, cells eventually reach a state where they can no longer divide, known as the Hayflick limit, essentially putting a biological clock on life itself. But not everyone agrees. Longevity researchers believe that aging is just another disease, one that can be slowed, stopped, or even reversed. Techniques like gene editing, stem cell rejuvenation, and cellular reprogramming are already showing promise in extending lifespan in animals. Some scientists believe that the first person to live to 150 or even 200 has already been born. But if there's no upper limit, what happens if people stop dying? Would society collapse under the weight of the immortal? Or is death simply a challenge we have yet to conquer? For now, the race to extend human life continues. But whether there's a finish line or a biological wall we can never break through remains one of the greatest mysteries of science. Are we bound by nature's limits, or are we about to rewrite the rules of life itself? Role of chaos in nature. Everything around you, your heartbeat, the weather, the stock market, even the path of a single drop of rain, follows one simple rule: chaos. At first glance, nature seems like a well-ordered system. The planets orbit predictably, seasons change on time, and life follows patterns of birth and decay. But beneath that order, chaos reigns. The smallest disturbance, a butterfly flapping its wings, a slight shift in ocean currents, can set off a chain reaction of unpredictable consequences. This is the essence of chaos theory, the idea that nature is far less stable and predictable than we like to believe. Weather is the perfect example. Meteorologists use vast amounts of data to predict storms, but beyond a few days, accuracy collapses. That's because even tiny changes in temperature, humidity, or wind speed can send the atmosphere spiraling into unexpected patterns. It's not randomness, it's chaotic determinism. The system follows rules, but those rules are so sensitive that tiny changes lead to vastly different results. Some scientists argue that chaos is not just a side effect of nature. It's the driving force behind evolution, climate patterns, and even human behavior. Without chaos, life might never have emerged in the first place. Mutations in DNA. Random, chaotic changes fuel evolution. Unpredictable disasters reshape ecosystems, forcing adaptation. Chaos doesn't destroy order, it creates it. But not everyone sees it that way. Some physicists believe that even the most chaotic systems are just highly complex but ultimately predictable. That if we had enough information, we could foresee every outcome. Others argue that true randomness exists, that some things are inherently unknowable. So does chaos mean nature is fundamentally unpredictable? Or are we simply missing the deeper patterns hidden beneath the apparent randomness? If the universe itself was born from chaos, does that mean we live in an unpredictable world? Or one that only appears that way until we learn how to read its patterns? Causes of neurodegenerative diseases. What if your own brain was working against you, slowly unraveling everything that makes you you? Neurodegenerative diseases like Alzheimer's, Parkinson's, and ALS are among the most terrifying conditions known to science. They strip away memory, movement, and identity itself. But despite decades of research, we still don't fully understand what causes them. Are they the result of genetics, environmental exposure, or a fundamental flaw in how the brain ages? The truth is, we're still piecing together the puzzle, and every answer only seems to bring more questions. For years, scientists believed misfolded proteins were the key culprit in diseases like Alzheimer's. Clumps of beta amyloid proteins build up in the brain, choking neurons and disrupting communication. In Parkinson's, it's Lewy bodies. In ALS, it's TDP-43. But here's the problem. Not everyone with these protein buildups develops the disease. Some people's brains are full of these misfolded proteins, yet they remain cognitively sharp. So if the plaques aren't the sole cause, what is? Another theory points to inflammation, the brain's own immune system turning against itself, attacking neurons instead of protecting them. There's also mounting evidence that viruses, gut bacteria, and even exposure to pollutants could be long-term triggers, slowly damaging the brain over decades. And then there's the most unsettling possibility. That neurodegeneration isn't caused by one single thing, but a combination of genetic predisposition, environmental triggers, and biological processes we don't yet understand. If we can crack the mystery of what truly causes neurodegenerative diseases, we could change millions of lives. But what if the answer isn't just one thing, but everything at once? Causes of autism. Autism is one of the most misunderstood conditions in science. We know it affects how people think, interact, and perceive the world. But what actually causes it? That question has fueled some of the most heated debates in medicine and neuroscience for decades. The leading theory has been genetics. Studies show that autism tends to run in families, and scientists have identified hundreds of genes linked to autistic traits. But here's the problem. No single gene causes autism. Some people with these genes never develop it, while others do without a clear genetic cause. So genetics alone can't be the whole story. That's where environmental factors come in. Researchers have explored everything from prenatal exposure to toxins, viral infections during pregnancy, complications at birth, and even differences in gut bacteria. Some studies suggest that certain chemicals or pollutants might slightly increase the risk, while others indicate that factors like maternal stress or nutritional deficiencies could play a role. But the tricky part? No single factor has been pinpointed as a definitive cause. And then there's the controversy. For years, misinformation linked vaccines to autism, a claim that's been thoroughly debunked by decades of research. Yet the myth persists, overshadowing real scientific inquiry into the condition. So what's the truth? Right now, the best explanation is that autism is caused by a complex interplay of genetics and environmental influences. Some scientists believe it's not just about risk factors, but about how the brain develops differently in early life. The real challenge isn't just understanding autism's causes, it's understanding the diverse ways it manifests. If autism isn't one thing but many, how do we even begin to define it? Interpretations of quantum mechanics. Reality might not work the way you think it does. In fact, the universe at its most fundamental level might not even decide what's real until someone observes it. This is the bizarre world of quantum mechanics, and for over a century, scientists have been trying to figure out what it really means. At the heart of this mystery is something called the wave function, a mathematical description of all the possible states a quantum particle can exist in. But here's where things get weird. A particle doesn't seem to choose a single state until it is observed. Before that, it exists in a superposition, essentially being in multiple places or states at once. The moment it's measured, boom, reality snaps into a definite state. But why? That's where the interpretations of quantum mechanics come in. Some physicists argue that wave function collapse is real, that the act of observation literally forces nature to pick an outcome. This is known as the Copenhagen interpretation, the standard view for decades. But others reject this idea completely. One alternative is the many worlds interpretation, which suggests that reality never chooses just one outcome. Instead, every possible outcome happens, splitting into separate universes. In one world, Schrödinger's cat is alive. In another, it's dead. This idea, once seen as science fiction, is now seriously debated. Then there's Bohmian mechanics, which says particles always have definite positions but are guided by a mysterious pilot wave that we can't directly observe. It makes quantum mechanics behave more like classical physics, just with a hidden layer beneath reality. Each interpretation raises its own paradoxes, and no one can agree on which, if any, is correct. But if quantum mechanics truly describes reality, then what is reality? And does the universe only exist when we look at it? Age of the Earth is old. But how old? The answer might seem obvious. Scientists say it's about 4.54 billion years old. But believe it or not, this question has been at the center of one of the most heated scientific and philosophical debates in history. For most of human civilization, people believe the Earth was relatively young. Ancient cultures, religious texts, and scholars estimated the planet to be only a few thousand years old. Even in the 17th century, James Ussher, an Irish archbishop, famously calculated that Earth was created in 4004 BCE using biblical genealogies as his guide. For centuries, this was widely accepted in the Western world. Then, geology came along and threw a wrench into everything. In the 18th and 19th centuries, scientists like James Hutton and Charles Lyell studied rock layers and fossils, realizing that the slow processes shaping the Earth, like erosion, mountain formation, and sedimentation, must have taken millions, if not billions, of years. The idea that the Earth was vastly older than previously thought gained traction. The real breakthrough came with radiometric dating in the 20th century. By measuring the decay of radioactive elements in rocks, scientists pinned down the age of Earth to about 4.54 billion years, give or take a few million. This method has been confirmed repeatedly using different dating techniques, from lunar samples to meteorites. But the controversy isn't entirely settled. Young Earth creationists reject these findings, arguing that radiometric dating is flawed and that the Earth is still only a few thousand years old. On the other hand, some researchers propose that our models of planetary formation might still be missing pieces. So is Earth really 4.54 billion years old? Almost all scientific evidence says yes. But what if we've barely scratched the surface of the planet's true history? Effectiveness of alternative medicine. Modern medicine saves lives. But what about alternative medicine? Some say it's a natural, holistic approach to healing that pharmaceutical companies don't want you to know about. Others argue that it's nothing more than pseudoscience preying on desperate people looking for hope. The debate over alternative medicine is one of the most heated in the world of health and science. Alternative medicine covers everything from herbal remedies and acupuncture to homeopathy and energy healing. Many traditional practices like Chinese medicine and Ayurveda have been around for thousands of years, far longer than modern pharmaceuticals. Supporters claim that these treatments work in harmony with the body, treating the root cause of illness rather than just symptoms. But here's where things get complicated. Scientific studies have tested many forms of alternative medicine, and the results are mixed. Some, like meditation and certain herbal supplements, have shown real benefits. Others, like homeopathy, which dilutes substances until not a single molecule remains, are scientifically implausible. The biggest issue? Many alternative treatments haven't been rigorously tested in controlled clinical trials, making it hard to separate placebo effects from real efficacy. Critics argue that relying on unproven treatments can be dangerous. If someone chooses herbs or energy healing over chemotherapy for cancer, the consequences can be fatal. But on the flip side, modern medicine doesn't have all the answers either. Alternative therapies often step in where conventional treatments fall short, especially in pain management and mental health. So does alternative medicine work? The answer isn't simple. Some treatments have merit. Others are outright scams. The real challenge is figuring out where to draw the line between ancient wisdom and modern science. Should we be more open-minded or more skeptical? Origin of language. If you're watching this, it means you understand language. But have you ever wondered, where did language actually come from? Who was the first human to string words together? And how did meaningless sounds evolve into the thousands of languages spoken today? The origin of language is one of the biggest unsolved mysteries in science, and it's more controversial than you might think. Some scientists believe language developed gradually, starting with basic sounds and gestures used by our ancient ancestors. Over time, these simple signals evolved into complex speech, but others argue that language emerged suddenly as a kind of cognitive leap. One day, early humans just started talking. One of the leading theories is the "oh wow" theory, which suggests that language began as an imitation of natural sounds, like early humans mimicking bird songs or animal calls. Another is the gestural theory, which claims that body language came first and spoken words were a later invention. Then there's the innateness hypothesis, championed by linguist Noam Chomsky, which suggests that the human brain is hardwired for language, and it's not something we simply invented. But here's the problem. Language doesn't fossilize. Unlike bones or tools, spoken words leave no physical trace, making it almost impossible to pinpoint when and how language began. Some believe it dates back hundreds of thousands of years, while others argue that true language, complete with grammar and structure, is only about 50,000 years old. The debate over language's origins isn't just about the past, it's about us. Is language something we created or something we discovered? If we could figure out how language began, would we finally understand what makes humans truly unique? Anthropocene Epoch. What if the most important geological era in Earth's history is happening right now? Some scientists argue that we've entered a brand new epoch, one not defined by natural forces but by us. It's called the Anthropocene Epoch, a term that suggests humans have altered the planet so drastically that we've left a permanent geological mark. But is this a real, scientifically valid period, or just an exaggerated way of saying we've made a mess of things? Traditionally, geological epochs are defined by massive planetary shifts, ice ages, asteroid impacts, the rise and fall of entire ecosystems. But in the last few centuries, human activity has dramatically reshaped the environment. Our cities, roads, and farmlands cover huge portions of the planet. We've extracted and burned billions of tons of fossil fuels. We've even created new materials like plastics and radioactive isotopes that will remain in Earth's crust for millions of years. Many scientists argue that these human-made changes are significant enough to mark a new geological era. They point to rising carbon dioxide levels, mass extinctions, and pollution as clear signs that the Anthropocene isn't just a concept, it's a reality. But not everyone agrees. Some geologists argue that while humans have certainly changed the world, these changes don't yet meet the strict criteria needed to define a new epoch. After all, Earth has been through dramatic shifts before, and our impact, while huge, might not be as permanent as we think. So are we truly living in the Anthropocene, or is this just a temporary phase in Earth's long history? If it is a new epoch, what kind of legacy are we leaving behind? Will future geologists look at our time and see innovation or catastrophe? Future of Earth's magnetic field. Earth's magnetic field is our invisible shield, protecting us from deadly cosmic radiation and solar storms. But what if I told you that this shield is weakening and might even flip entirely? The future of Earth's magnetic field is one of the biggest scientific mysteries, and it's a topic filled with controversy, speculation, and a lot of unanswered questions. Every few 100,000 years, Earth's magnetic poles switch places. North becomes south, and south becomes north. It's happened many times in the past, but here's the concerning part. Some scientists believe we're overdue for the next big reversal. Right now, the magnetic field is weakening, especially in a region known as the South Atlantic Anomaly, an area where satellites and spacecraft experience strange, unpredictable failures. Some researchers think this could be an early sign that a pole reversal is coming. If that happens, Earth's protective magnetic shield could temporarily collapse, exposing us to increased radiation from the sun and deep space. But here's where the debate begins. Some scientists argue that while the magnetic field is shifting, reversals take thousands of years to complete, meaning we might not see any major effects in our lifetime. Others warn that if the weakening continues at its current rate, we could face disruptions in power grids, GPS systems, and even an increase in cancer rates due to higher radiation exposure. So, is a magnetic apocalypse on the horizon? Or is this just another natural fluctuation? Will future generations live in a world where compasses point south instead of north? If Earth's magnetic shield does fail, how will we protect ourselves? Role of asteroids in mass extinctions. 66 million years ago, a rock from space changed life on Earth forever. A single asteroid, about 6 miles wide, crashed into what is now Mexico's Yucatan Peninsula, setting off a global catastrophe that wiped out the dinosaurs. But was this the only mass extinction caused by an asteroid? Or could Earth's history be shaped by more cosmic impacts than we realize? The idea that asteroids have played a major role in Earth's mass extinctions is both widely accepted and highly debated. The Chicxulub impact is the most famous example. Its aftermath was apocalyptic. Firestorms ignited across continents. Tsunamis swept coastlines. A thick cloud of debris blocked out the sun for years, triggering a global winter that collapsed ecosystems. But what if this wasn't an isolated event? Some scientists believe asteroids have been responsible for multiple extinction events, not just the one that took out the dinosaurs. Evidence suggests that a different impact may have contributed to the Permian-Triassic extinction, the most devastating mass extinction in history, wiping out 90% of marine species and 70% of land animals. However, not everyone agrees. Some argue that volcanic activity, climate shifts, or even mysterious geological events played a bigger role in these ancient die-offs. The controversy lies in the difficulty of proving these impacts. Unlike the dinosaur-killing asteroid, many older craters have been eroded or buried over time, making it hard to connect them to extinction events. Could a yet undiscovered impact site be waiting beneath the Earth's surface, holding secrets to another great die? And here's the unsettling question. If asteroids shaped Earth's past, could they shape its future? NASA and other space agencies are tracking thousands of near-Earth objects, but what if the next extinction-level impact is already on its way? Would we be able to stop it? Or would we be the next species erased by the cosmos? Mechanisms of climate change. Earth's climate is changing. But why? Is it natural, or are we the ones driving it? This question has sparked one of the most heated scientific debates of our time. Some argue that the planet has always gone through cycles of warming and cooling, while others point to overwhelming evidence that human activity is the dominant force behind modern climate change. So what's really happening? At its core, climate change is a disruption in the balance of Earth's climate system. The leading explanation focuses on the greenhouse effect, a natural process where gases like carbon dioxide and methane trap heat in the atmosphere, keeping the planet warm enough for life. The problem? Since the Industrial Revolution, humans have been pumping unprecedented amounts of these gases into the air, trapping more heat than ever before. This leads to rising temperatures, shifting weather patterns, and an increase in extreme events like hurricanes, droughts, and wildfires. But not everyone agrees. Some skeptics argue that solar cycles, ocean currents, and volcanic activity play a larger role in climate fluctuations. After all, Earth has experienced ice ages and warming periods long before humans existed. However, the data shows that today's warming is happening faster and more dramatically than any natural cycle we've ever seen. The controversy deepens when it comes to solutions. Do we need radical changes in energy, industry, and consumption? Or can technology save us? Some believe geoengineering, like injecting particles into the atmosphere to reflect sunlight, could be a last resort, but that comes with unpredictable risks. So what happens next? Are we heading toward a climate catastrophe, or can we still reverse the damage? And if we don't act now, will future generations look back and wonder, why didn't they do something while they still had the chance? The existence of exoplanets. Habitability. We now know that planets outside our solar system, exoplanets, are everywhere. But how many of them could actually support life? Could there be another Earth out there? Or is our planet truly one of a kind? The idea of habitable exoplanets isn't science fiction anymore. Since the 1990s, astronomers have discovered thousands of these distant worlds, some eerily similar to Earth. The Goldilocks zone, where a planet is just the right distance from its star for liquid water to exist, has become a major focus in the search for life. Kepler 442b, TRAPPIST-1e, and Proxima Centauri b are just a few of the top contenders. But habitability is about more than just water. What about atmosphere, magnetic fields, or even the right kind of chemistry? This is where the debate begins. Some scientists argue that Earth-like conditions might be extremely rare. They point to Venus, a planet once thought to be habitable but turned into a hellscape due to runaway greenhouse gases. Others believe that life could exist in conditions completely unlike Earth's, thriving in high radiation, deep oceans, or even frozen landscapes. If extremophiles on Earth can survive in boiling vents and acidic lakes, why not elsewhere? Then there's the big question. Even if a planet is habitable, does that mean it's inhabited? The conditions for life may be common, but the emergence of life itself could be incredibly rare, or maybe the opposite is true. Maybe the universe is teeming with life, and we just haven't looked in the right places yet. So, are we truly alone? Or are there other civilizations looking up at their own skies, asking the exact same question? Nature of pulsars. In the 1960s, astronomers detected a mysterious repeating radio signal coming from deep space. So precise, so rhythmic, that some believed it could be a message from aliens. But what they had actually discovered was something just as strange: pulsars. Pulsars are neutron stars, the collapsed cores of massive stars that went supernova. They spin at incredible speeds and emit beams of electromagnetic radiation. Imagine a cosmic lighthouse, but instead of guiding ships, it sweeps pulses of energy across the universe, flashing every time the beam crosses Earth's view. Some pulsars spin at thousands of rotations per second, making them some of the most extreme objects in existence. But here's where the controversy begins. How do pulsars emit such intense, focused beams of energy? The exact mechanisms behind their emission are still not fully understood. Scientists know that powerful magnetic fields are involved, but the precise details remain elusive. Some models suggest charged particles moving along magnetic field lines generate the pulses, while others propose more exotic explanations involving quantum effects and extreme gravity. Pulsars have also been used to test Einstein's theory of general relativity, acting as natural cosmic clocks. But what if our understanding of them is flawed? If new physics is lurking in the behavior of pulsars, it could mean our entire model of space-time needs revision. Are pulsars simply nature's most accurate clocks? Or could they be hiding deeper, unknown forces of the universe? What else might be waiting to be discovered in these spinning remnants of dead stars? Acceleration of the universe. The universe isn't just expanding, it's speeding up, and that's a problem. For decades, scientists assumed that gravity would eventually slow down the expansion of the universe. It made sense. After all, everything that expands under gravity eventually loses momentum. But in 1998, astronomers made a shocking discovery. Instead of slowing down, the universe is accelerating. The farther away a galaxy is, the faster it's moving away from us. Some invisible force, is pushing the fabric of space itself apart. This discovery turned physics upside down. To explain it, scientists introduced dark energy, a mysterious form of energy that makes up nearly 70% of the universe. Unlike gravity, which pulls things together, dark energy does the opposite. It repels, forcing space to stretch at an increasing rate. But here's the issue. No one knows what dark energy actually is. Is it a fundamental property of space, a hidden force embedded in quantum mechanics, or something even stranger, something that could rewrite our understanding of physics? The controversy is massive. Some physicists believe dark energy is just an illusion, the result of an incomplete theory of gravity. Others argue that the accelerating universe hints at a multiverse, where different regions of reality follow different rules. Some even speculate that acceleration could be a sign that the universe has an expiration date, that one day it could tear itself apart in a big rip. If the universe is truly accelerating, where is it going? And more importantly, what happens when it gets there? Nature versus nurture. Are you the way you are because of your genes or because of your experiences? The age-old debate of nature versus nurture asks a fundamental question. What truly shapes us? Are intelligence, personality, and behavior wired into our DNA, or are they sculpted by the environment we grow up in? This debate has fueled scientific controversy for centuries, and the answer may be far more complicated than either side expected. Supporters of nature argue that genetics lay the foundation for who we are. Your height, eye color, and even risk for certain diseases are all encoded in your DNA. But beyond the physical, research suggests that genetics may also play a role in things like temperament, mental disorders, and even intelligence. Twin studies, where identical twins separated at birth show eerily similar traits despite growing up in different environments, have provided some of the strongest evidence for this argument. On the other hand, the nurture camp insists that genetics only provide a starting point. Environment, upbringing, education, and experiences shape a person far more than their DNA. A child's development can be dramatically influenced by parenting styles, nutrition, social interactions, and cultural norms. Some scientists argue that even IQ, often thought to be largely genetic, can be significantly improved or suppressed depending on external factors like education and access to resources. But the real controversy? It's likely not nature or nurture, but both, deeply intertwined. Modern genetics shows that experiences can actually alter gene expression in a process called epigenetics, meaning that even inherited traits can be modified by life experience. So if both nature and nurture play a role, the real question becomes, how much of who we are is in our control? And if we could alter the balance, enhancing nature with nurture, how far should we go? Mechanisms of pain. Perception. Pain isn't real, at least not in the way you think. It's easy to assume pain is just body's way of saying, hey, something's wrong. But what if I told you that pain isn't a direct result of injury, but a complex illusion crafted by your brain? Here's where things get strange. There are cases where people suffer extreme injuries, like soldiers in battle, yet feel no pain until much later. On the flip side, some people experience phantom limb pain, feeling excruciating sensations in a limb that no longer exists. How is that possible? Pain perception is not just a simple nerve-to-brain transmission. It's a negotiation between your nervous system and your brain. The gate control theory suggests that pain signals travel through a gate in the spinal cord, and that gate can be opened or closed depending on context, emotion, and even expectation. If you're distracted or flooded with adrenaline, your brain might close the gate, reducing pain. But if you expect pain or feel anxious, the gate stays wide open, amplifying the sensation. And then there's the placebo effect, where people experience real pain relief from fake treatments. This suggests that pain isn't just about nerves, it's about belief. But if pain is subjective, can we fully trust our own perception of suffering? Or is our brain playing tricks on us, shaping reality in ways we don't even realize? Placebo effects. What if I told you your brain could heal your body without any real medicine? The placebo effect is one of the strangest and most controversial phenomena in medical science. People take sugar pills, receive fake surgeries, or get saline injections, and yet they genuinely feel better. Their pain fades, and sometimes their bodies even heal. But how? At its core, the placebo effect reveals the incredible power of belief. If your brain expects a treatment to work, it can trigger real physiological changes, releasing pain-relieving chemicals, boosting immune function, even altering heart rate and blood pressure. In some cases, placebos have been nearly as effective as actual medication. This is where things get messy. If belief alone can trigger healing, do we need the medicine at all? Some argue that harnessing the placebo effect could revolutionize medicine, reducing reliance on drugs. Others warn that it's just a mind trick, masking symptoms without addressing real disease. And then there's the ethical dilemma. Should doctors prescribe fake treatments if they genuinely help patients? What happens when the effect wears off, or when real medication is ignored in favor of belief-based healing? If the mind can create relief without medicine, what else is it capable of? And if we can harness the placebo effect, could we one day use our own brains to heal ourselves? No prescription required. Localization of brain function. Is your brain just a collection of interchangeable parts? Or is each region a specialist with a job it refuses to share? For centuries, scientists have debated whether different areas of the brain are responsible for specific tasks, a concept known as localization of brain function. This idea suggests that your ability to speak, move, and even feel emotions isn't spread out evenly, but instead mapped to precise regions within your brain. The theory took shape in the early 1800s with phrenology, where bumps on the skull were thought to indicate personality traits. That turned out to be complete nonsense. But the broader idea of localized brain function stuck. Fast forward to the 19th century, and neurologists like Paul Broca discovered that damage to one specific brain area led to speech impairments, supporting the idea that language lives in one part of the brain, not everywhere. Today, neuroscience supports localization up to a point. Brain scans show that movement, vision, and memory all light up distinct areas, meaning different regions have specialized roles. But then there's the controversy. The brain is far more flexible than we thought. If one area is damaged, other regions can often adapt and take over its function. This plasticity challenges the strict version of localization, making scientists question just how specialized the brain really is. So, is your brain an intricate circuit board with neatly labeled sections? Or is it a dynamic, ever-changing network that can reroute itself when needed? And if functions aren't truly trapped in specific areas, what does that mean for how we think about intelligence, learning, and even consciousness itself? Neurotransmitters in mental disorders. What if the difference between happiness and depression, clarity and confusion, or even sanity and madness all came down to tiny chemicals in your brain? For decades, scientists have argued over the role of neurotransmitters in mental disorders. The idea is simple. Neurotransmitters are chemical messengers that carry signals between brain cells. And when they're imbalanced, things go wrong. Too little serotonin, and you might experience depression. Too much dopamine, and you could suffer from hallucinations. Mental health disorders in this view are largely biochemical problems, things that can, in theory, be fixed with medication. But not everyone agrees. Some researchers argue that reducing mental illness to just a chemical imbalance is far too simplistic. The brain is incredibly complex, and mental disorders involve a mix of genetics, environment, and life experiences. Studies have even shown that people with depression don't always have lower serotonin levels, raising questions about whether neurotransmitter imbalances are truly the root cause or just a symptom of deeper issues. This debate has massive real-world consequences. If mental illness is just a chemical imbalance, then medication should be the perfect cure. But if the problem is more complex, rooted in trauma, neuroplasticity, or social factors, then relying solely on drugs might not be enough. So do neurotransmitters really hold the key to understanding mental disorders? Or have we oversimplified the brain's mysteries? And if we do find a perfect balance of chemicals, would that mean we could one day engineer perfect mental health? Memory formation. Your memories might be lying to you. We tend to think of memory as a mental video recorder, storing our past exactly as it happened, ready to be played back whenever we recall it. But science tells a very different story. Memories aren't stored like files in a computer. They're reconstructed, pieced together every time you remember them. And each time, details can change. This means that the memories you trust the most, the ones that feel the clearest, could be the most distorted. Memory formation is one of neuroscience's greatest mysteries. We know it involves neurons strengthening their connections, a process called synaptic plasticity. We also know that the hippocampus, a small seahorse-shaped structure in the brain, plays a crucial role in converting short-term memories into long-term ones. But beyond that, things get murky. Some researchers argue that memory is like a biological web, with new experiences constantly altering old ones. Others believe that memories might not be stored in a single place, but distributed throughout the brain, making them incredibly resilient and incredibly vulnerable to distortion. The controversy deepens when we look at memory manipulation. Studies show that false memories can be implanted. People can be made to vividly recall events that never happened. This has major implications for everything from eyewitness testimony to therapy and even personal identity. If our memories shape who we are, but they can be rewritten, what does that say about our sense of self? So if memory is more fragile and unreliable than we think, how much of our past is real? And more importantly, if we had the power to edit our memories, would we use it? Role of genetics versus environment. Are you born to be who you are, or are you shaped by the world around you? This question has fueled one of the longest-running debates in science: nature versus nurture. Are intelligence, personality, and even success determined by genetics? Or do environment and experience mold us into who we become? The answer is far from simple, and the debate is anything but settled. On one side, genetic determinists argue that DNA is the blueprint of our lives. Studies on identical twins who share the same DNA show striking similarities in intelligence, temperament, and even behaviors even when raised apart. This suggests that genetics lay the foundation for much of who we are. Traits like height, eye color, and susceptibility to certain diseases are clearly inherited. So why not personality or intelligence? But on the other side, environmentalists push back. They argue that genes may set the stage, but experience writes the script. A child raised in a stimulating, supportive environment is far more likely to thrive than one raised in neglect, no matter their genetic potential. The impact of trauma, education, and culture all point to the massive role environment in shaping individuals. Studies even show that early childhood experiences can alter gene expression, meaning nurture can modify nature at a fundamental level. So where does that leave us? The truth likely lies somewhere in between. Genes may give us the ingredients, but the environment determines how the recipe turns out. But if that's the case, how much of who you are was truly your choice? Culture shaping behavior. What if your decisions, beliefs, and even emotions aren't entirely your own, but shaped by something much bigger than you? The idea that culture shapes behavior is both obvious and deeply controversial. From the way we speak and dress to the way we think about morality, success, or even happiness, culture acts like an invisible force, molding us in ways we rarely question. But just how much does culture dictate human behavior? And how much free will do we really have? Consider individualistic versus collectivist cultures. In Western societies like the US and many European countries, personal success and independence are celebrated. You're expected to follow your dreams and stand out. But in many Eastern cultures, cooperation, family honor, and social harmony take priority over individual desires. Studies show that people raised in collectivist cultures are more likely to conform, while those from individualist cultures tend to challenge authority and take risks. Even something as simple as perception is influenced by culture. Research has shown that Westerners tend to focus on objects, while East Asians focus on the relationships between them. That means two people from different cultures could look at the same scene but notice completely different things. So why is this controversial? Some argue that biology plays a bigger role than culture, pointing to human universals like emotions and survival instincts. Others argue that cultural conditioning is so strong that it can override even basic human tendencies, influencing everything from morality to cognitive biases. If culture shapes behavior this much, then what happens when cultures collide? Does globalization mean we are becoming more alike? Or will cultural differences remain as strong as ever? And if we understand how culture shapes us, can we ever truly escape its influence? Safety of nuclear power. Nuclear power is either humanity's greatest energy solution or a ticking time bomb. It depends on who you ask. For decades, the debate over the safety of nuclear power has raged on, dividing scientists, policymakers, and the general public. On one side, nuclear energy is hailed as one of the cleanest, most efficient sources of power we have. Unlike fossil fuels, it doesn't pump carbon dioxide into the atmosphere. Unlike solar or wind, it provides a steady, uninterrupted power supply. But then there's the other side. The disasters, the radiation, the terrifying images of Chernobyl and Fukushima. So which is it? A climate-friendly miracle or a catastrophe waiting to happen? Advocates argue that modern nuclear reactors are incredibly safe compared to the early designs of the Cold War era. Fourth-generation reactors and small modular reactors are designed with passive safety features, meaning they can shut down automatically if something goes wrong. No human intervention needed. In fact, per unit of energy produced, nuclear power has caused fewer deaths than coal, oil, or even hydropower. But critics warn that even one meltdown can have devastating consequences. The Fukushima disaster in 2011, triggered by a tsunami, released radioactive material into the environment, causing mass evacuations and long-term health concerns. And then there's the issue of nuclear waste, highly radioactive material that remains dangerous for thousands of years. Where do we store it? And can we guarantee future generations will keep it contained? With the climate crisis escalating, some argue we can't afford to ignore nuclear energy. Others insist the risks are too great. So is nuclear power the key to a sustainable future? Or is it simply too dangerous to bet on? And if we don't embrace it, what's the alternative? Future of transportation. The way we move from place to place is on the verge of a revolution, but no one can agree on what comes next. Will we zip through cities in autonomous electric cars, fly across countries in hypersonic jets, or maybe even teleport? While that last one might still be science fiction, the future of transportation is a hotly debated topic with no clear answer. Some believe we're headed for a world of hyperloops and flying taxis, while others argue we're overhyping the possibilities and that real change is much further away than we think. One of the biggest ideas in transportation right now is electric and autonomous vehicles. Companies like Tesla and Waymo promise that self-driving cars will reduce accidents, ease traffic, and change urban landscapes. No more parking lots, no more traffic jams, just seamless, efficient transport. But skeptics point out that full autonomy is proving to be far more difficult than expected. The technology still struggles with unpredictable human drivers, and ethical dilemmas like how an AI should react in an unavoidable crash raise serious concerns. Then there's high-speed transit. Elon Musk's Hyperloop concept proposes passengers shooting through vacuum tubes at over 600 miles per hour, cutting travel times drastically. Sounds great, except the physics, infrastructure costs, and safety concerns make many experts doubtful it will ever be widely implemented. Meanwhile, some say we should focus on high-speed rail, like Japan's bullet trains, proven technology that many countries still refuse to invest in. And let's not forget air travel. Supersonic jets are making a comeback, promising New York to London in under 4 hours. But with climate concerns growing, will air travel even be a viable long-term solution? With so many possibilities and limitations, the future of transportation is still up for debate. Will we finally break free from traffic and long commutes? Or are we overpromising what's actually possible? Role of microbiota. Your body isn't just you. It's a thriving metropolis for trillions of microscopic organisms. And strangely enough, they might control way more than we ever imagined. For years, we thought bacteria were just disease-causing invaders. But now scientists are discovering that the microbiota, the vast collection of bacteria, viruses, and fungi living inside us, might be one of the most important yet overlooked factors in human health. Some researchers even suggest that these microbes influence everything from digestion to mood, immunity, and even brain function. But just how much power do they really have? The microbiota's role in digestion is well understood. These microscopic helpers break down food, synthesize vitamins, and regulate metabolism. But here's where things get weird. Some studies suggest they might also be affecting mental health. Experiments on mice have shown that transferring gut bacteria from an anxious mouse into a calm one can make the calm mouse anxious. If similar mechanisms apply to humans, it could mean gut bacteria are influencing depression, anxiety, and even personality traits. The controversy? Some scientists argue that the microbiome is overhyped. While its role in digestion is clear, the idea that gut bacteria might be steering thoughts and emotions is still unproven. The brain is vastly complex, and critics argue that microbiota research is still in its infancy, with many claims lacking solid evidence. If microbiota truly shape our bodies and minds, could we one day edit our microbial populations to boost mood, prevent disease, or even enhance intelligence? Or are we just scratching the surface of something far more complex than we realize? Function of sleep. You spend a third of your life unconscious. But why? For something so essential, sleep is still one of science's biggest mysteries. We know we need it. Go too long without it and the brain starts shutting down. But what exactly is happening when we sleep? Why do we dream? And could we one day engineer a world where sleep is no longer necessary? One of the leading theories is that sleep acts as a biological reset button. It's when the brain clears out waste, consolidates memories, and repairs cells. But here's where things get strange. Scientists still don't fully agree on what sleep's most critical function actually is. Some believe it's mostly about memory consolidation, turning experiences into long-term knowledge. Others argue that sleep is mainly about removing toxins from the brain, preventing neurodegenerative diseases like Alzheimer's. And then there's the idea that sleep is simply an evolutionary leftover, an inefficient way for organisms to conserve energy. But some researchers are skeptical of these explanations. If sleep is purely about the brain, then why do even the simplest organisms sleep? Fruit flies, jellyfish, even worms experience sleep-like states despite having no complex cognitive functions. Could it be something even deeper? A fundamental biological process we have yet to understand. Then comes the most controversial question. Could we hack sleep? If we could figure out exactly what makes sleep so essential, could we develop ways to replace it entirely? What would happen if humans no longer needed to sleep at all? Would we become more productive? Or would our minds collapse without that nightly reset? Group selection. Could evolution favor the survival of the group rather than just the individual? For decades, the dominant idea in evolutionary biology has been natural selection at the level of individuals or genes. The selfish gene model, famously popularized by Richard Dawkins, argues that organisms behave in ways that maximize the survival of their own genetic material. But an alternative theory, group selection, suggests that sometimes evolution works at a higher level, favoring traits that benefit a group even if they disadvantage an individual. The idea is simple. Imagine two competing groups. One is made up of selfless, cooperative individuals who work together for the common good. The other is full of selfish individuals who prioritize their own survival at the expense of the group. Even if selfish individuals within a group might outcompete their altruistic peers, the entire cooperative group could outcompete the selfish one over time. Natural selection might favor groups with altruistic behavior, even if individuals within those groups don't directly benefit. But here's the controversy. Many scientists argue that group selection is unnecessary, that all forms of cooperation from ants to humans can be explained by kin selection and reciprocal altruism. In other words, we don't need to invoke group-level evolution because cooperative behaviors already help an individual's genes survive, either through relatives or strategic alliances. Yet some evolutionary biologists, like E.O. Wilson, have pushed back. They argue that group selection could explain behaviors that gene-level selection struggles with, like extreme self-sacrifice, eusocial insects, and large-scale human cooperation. So is evolution just selfish genes doing their thing? Or does nature sometimes play the long game, shaping entire groups for survival? If group selection is real, it could redefine how we understand everything, from human societies to the origins of morality itself. Role of mitochondria in aging. What if the secret to aging isn't in your DNA, but in tiny power plants inside your cells? For decades, scientists have searched for the cause of aging, why our bodies gradually break down over time. One leading theory points to an unexpected culprit: mitochondria. These microscopic structures are responsible for producing energy in almost every cell in your body. But as you age, they start to falter, and some researchers believe that this decline is what ultimately drives aging itself. Here's how it works. Mitochondria generate energy through a process called cellular respiration, but in doing so, they also produce free radicals, highly reactive molecules that damage cells, proteins, and even DNA. Over time, this oxidative stress accumulates, impairing mitochondrial function and triggering a cascade of cellular decline. The more damaged your mitochondria, the less energy your cells can produce, leading to everything from muscle loss to cognitive decline. But not everyone agrees that mitochondria are the main cause of aging. Some scientists argue that mitochondrial dysfunction is just a symptom of a larger process, not the root cause. Others believe that the body has natural repair mechanisms that counteract mitochondrial damage, and that aging is driven by a combination of genetic, metabolic, and environmental factors. Still, arrow of time. Time only moves forward. You age. You remember the past, but not the future. And no matter how much you wish otherwise, a broken egg never unbreaks. But why? The fundamental laws of physics don't actually require time to have a direction. So what forces time to march forward, never backward? This is the mystery of the arrow of time, one of the most puzzling questions in physics. At the core of this mystery is the second law of thermodynamics, which states that entropy always increases. Entropy is a measure of disorder, and the universe, it seems, is always moving towards more chaos. Ice melts, stars burn out, everything decays. This is the closest thing physics has to a rule that gives time a direction. The past is orderly, the future is messy. But here's the problem. The laws of physics work just as well in reverse. If you filmed an atom bouncing around and then played it backward, it would still obey all the known equations of motion. So why doesn't the universe behave like this on a larger scale? Why don't we see shattered glass reassemble or spilled coffee leap back into the cup? One explanation is that the Big Bang set the universe in an extremely low entropy state, like a neatly stacked deck of cards. Over time, disorder has increased, creating the illusion of time flowing forward. But this raises another question. Why did the Big Bang start in such an ordered state to begin with? And could time ever run backward under the right conditions? Some physicists speculate that in a distant, contracting universe, time could reverse, creating a mirror reality where everything runs backward. If that's true, then time isn't a fundamental force. It's just an effect of entropy. And if entropy could be controlled, could time be manipulated too? Cosmological Multiverse. What if the universe isn't the only one? What if, beyond the limits of what we can see, there are countless other universes, each with its own galaxies, laws of physics, and maybe even alternate versions of you? This is the idea behind the cosmological multiverse, a theory that suggests our universe is just one of many, part of a vast, ever-expanding cosmic landscape. The idea stems from cosmic inflation, the rapid expansion that took place moments after the Big Bang. Some physicists like Alan Guth and Andre Linde propose that inflation didn't just create our universe. It never stopped, continuing to spawn new universes forever. Each universe, or bubble, could have different physical constants, meaning the laws of nature we take for granted, like gravity or electromagnetism, might work completely differently elsewhere. But here's where things get controversial. There's no direct evidence. The multiverse isn't something we can observe, measure, or test, which raises a huge question. Is it even science? Critics argue that without experimental proof, the multiverse is nothing more than philosophical speculation dressed up in physics. Others counter that if inflation theory is correct, and much of modern cosmology relies on it, then the multiverse is an unavoidable consequence. If true, it would change everything. It could explain why our universe seems so perfectly fine-tuned for life. In an infinite multiverse, there would naturally be some universes where conditions are just right. But if we can never interact with these other realities, does it really matter? Is the multiverse a profound scientific breakthrough waiting to be understood, or just an escape hatch for ideas we can't explain? Until we find evidence, the answer remains beyond our universe, and maybe beyond our reach. Plate tectonics. The ground beneath your feet is moving, not fast enough to notice, but slowly, relentlessly reshaping continents, raising mountains, and tearing open oceans. This is plate tectonics, the unceasing motion of Earth's crust that explains why earthquakes shake cities, why volcanoes erupt, and why entire land masses drift apart over millions of years. But for a long time, scientists dismissed this idea as pure nonsense. Before the 20th century, continents were believed to be fixed in place. Then came Alfred Wegener, a German meteorologist who noticed something odd. The coastlines of South America and Africa fit together like puzzle pieces. He proposed that continents weren't fixed at all, but drifted across Earth's surface over time. His idea, called continental drift, was ridiculed. He had no explanation for how massive land masses could move. It just didn't seem possible. Decades later, under the ocean, geologists discovered mid-ocean ridges, huge underwater mountain chains where new crust was forming. As molten rock rose from beneath, it pushed old crust away, slowly driving the continents apart. This discovery confirmed what Wegener had theorized all along. Earth's surface wasn't fixed. It was broken into giant plates constantly shifting and colliding. But not everyone accepted it immediately. Some scientists argued that if plates are always moving, why isn't the Earth ripping itself apart? Others questioned whether subduction, where one plate sinks beneath another, could actually recycle crust fast enough to balance the process. Even today, there are debates about what drives the movement of these plates. Is it the heat from Earth's core, or something even deeper? Plate tectonics explains earthquakes, volcanoes, and even the rise and fall of ancient supercontinents. But if Earth's crust is always shifting, what does that mean for our future? Could entire continents one day collide again, forming a new supercontinent? And if so, what will the world look like millions of years from now? Mind, origin of the moon. Look up at the night sky and you'll see it. The moon, Earth's closest companion. But have you ever wondered where it actually came from? For something that's been around for over 4 billion years, its origin remains one of the most debated mysteries in science. For decades, scientists have tried to piece together the moon's origin story, but no single explanation fits perfectly. Some early theories suggested it simply formed alongside Earth from the same swirling cloud of dust and gas. Others argued that Earth captured the moon, pulling in a wandering rock from space. The problem: neither fully explains why the moon's composition is eerily similar to Earth's crust, yet missing certain elements. Then came the giant impact hypothesis, now the leading theory. According to this idea, around 4.5 billion years ago, a Mars-sized planet, Gaia, crashed into the young Earth. The collision was so violent that molten rock and debris were blasted into space, eventually coalescing to form the moon. This explains why the moon shares Earth's chemistry, but with key differences. Volatile elements were likely burned off in the fiery impact. But even this widely accepted theory has problems. Some scientists argue that if Theia truly existed, why haven't we found distinct chemical traces of it? Others suggest alternative ideas, like the moon forming from multiple smaller impacts or even being spun out of Earth itself due to extreme rotation, a theory once favored but now largely dismissed. No matter which theory turns out to be right, the moon's origin is more than just a cosmic curiosity. It could hold the key to understanding Earth's past and even the formation of other planets. So was it an impact, a cosmic accident, or something we haven't even thought of yet? The answer may be waiting on the moon itself. Mechanisms of photosynthesis. Without photosynthesis, life as we know it wouldn't exist. Every breath of oxygen, every bite of food, every towering tree, all of it depends on this biological magic trick that turns sunlight into energy. But here's the catch. We still don't fully understand how it works. Sure, we know the basics. Plants take in carbon dioxide and water, use sunlight to trigger a series of chemical reactions, and release oxygen while producing glucose. Simple enough, right? Not even close. The molecular machinery inside plants is mind-bogglingly complex, operating with near-perfect efficiency far beyond anything human engineers have ever built. And here's where the real controversy starts. For years, scientists believed that photosynthesis followed a straightforward step-by-step pathway. Light gets absorbed, energy gets transferred, and chemical bonds get formed. But recent discoveries suggest that quantum mechanics may be at play. Some studies indicate that plant cells don't just transfer energy like a baton in a relay race. They may use quantum superposition to explore multiple pathways at once, choosing the most efficient route. If true, this would mean that plants have unknowingly been harnessing the bizarre rules of quantum physics for billions of years. Not everyone is convinced. Skeptics argue that quantum effects are too delicate to survive in the messy, warm environment of a living cell. Others insist that classical physics alone is enough to explain photosynthesis without the need for exotic quantum phenomena. The debate continues, with experiments pushing the limits of what we thought plants were capable of. If we could unlock the full potential of photosynthesis, we could revolutionize energy production, perhaps even creating artificial leaves that could power entire cities. But before we get there, one question remains. Have plants mastered physics in ways we're only beginning to understand? Quantum effects in chemistry. Most of us think of chemistry as predictable. You mix two chemicals and they react. Simple. But what if I told you that some of the most important chemical reactions might be happening because of quantum physics? That at the tiniest scales, the world of molecules isn't as straightforward as it seems? This idea that quantum effects play a fundamental role in chemistry is both fascinating and controversial. Traditional chemistry operates on the laws of classical physics. It explains how atoms bond, how reactions occur, and how energy moves through molecules. But at extremely small scales, things start to get weird. Particles don't behave like tiny billiard balls. They behave like waves, existing in multiple places at once, tunneling through barriers they shouldn't be able to cross, and even choosing the most efficient reaction pathways, as if they knew the best route in advance. One of the most intriguing examples of this is enzyme catalysis, the process that speeds up chemical reactions inside your body. Some researchers believe that enzymes might be using quantum tunneling, a bizarre phenomenon where particles slip through energy barriers instead of climbing over them. If true, this means your body's chemistry relies on quantum tricks to function efficiently. And then there's photosynthesis. Some experiments suggest that the way plants transfer energy might involve quantum coherence, where energy exists in multiple states at once, finding the quickest route to the reaction center. If plants are secretly quantum physicists, what else in nature might be using these effects? Of course, skeptics argue that biological systems are too chaotic, too warm for delicate quantum phenomena to survive. They believe classical physics alone can explain chemistry. But the more we study these effects, the more we realize nature might be playing by quantum rules in ways we never imagined. If quantum mechanics is deeply embedded in chemistry, It could redefine how we think about everything, from drug design to renewable energy. But the real question is, if life itself is quantum, what else are we missing? Nature of chemical bonding. What if I told you that the very glue holding the universe together, chemical bonds, is still not fully understood? You'd think that by now we'd have figured out exactly how atoms stick together, right? Well, not quite. The nature of chemical bonding remains one of the most debated and mysterious topics in chemistry. At first glance, chemical bonds seem simple. Atoms share, steal, or swap electrons, forming stable molecules. This is what we were all taught in school. Ionic bonds involve electron theft. Covalent bonds involve sharing. And metallic bonds create electron seas. Case closed, right? Not exactly. Take covalent bonding, a fundamental concept. Traditional chemistry says atoms share electrons to form stable pairs. But quantum mechanics throws a wrench into this explanation. Electrons don't orbit like tiny planets. They exist in fuzzy probability clouds. In reality, when two atoms bond, their electrons don't just pair up in a straightforward way. They enter a strange quantum superposition, where they are spread out over both atoms at once. So do molecules even have bonds in a classical sense, or are they just complex quantum interactions? And then there's the mystery of the hydrogen bond.